All right, Steve, let us talk about computers. How far back do we have to go to understand this?
Well,
when you say first principles, are you talking silicon? What are we talking about?
Before that, actually, if we wind ourselves back in a time, we get into our Wayback Machine, and want to understand the first successful computers, and I'm talking about, frankly, the PDP DEC machines. There was Honeywell and Burroughs, Digital Equipment Corporation, IBM. These early machines were pre-integrated circuit, so there wasn't this notion of multiple components that could be mass produced. That was an amazing breakthrough, which is very easy to take for granted. I mean, Lord knows everybody listening to this has integrated circuits surrounding them, and I would say throughout the day we're surrounded by integrated circuits doing different things. But before it was possible to integrate different types of components onto a single piece of silicon, which allowed then mass production. All of these components were separate, and it was the separateness of them and the need to interconnect them which put a tremendous limiting factor on the feasible complexity of these early machines. So what I want to do is really start at the beginning with, if you have resistors and transistors, how do you create logic from that? How, we know the computers use ones and zeros. There were computers, analog computers, which people tinkered with, which for a while they had the benefit of being able to, with a lower degree of accuracy, do things in the analog world where currents and voltages conveyed meaning. They were able to do things far more easily than digital computers of the era within the same time frame, except that what ended up happening was we needed more accuracy. Things like temperature could affect the accuracy of an analog computer. And so it turned out that just treating everything as collections of binary information, ones and zeros, even though you needed a lot of them in order to get the same resolution that you could get sort of for free with a voltage on a wire, you could represent that voltage with a sufficiently large number of ones and zeros and get the resolution you needed, and also get absolute accuracy that would not drift over time. You didn't have to worry about calibration and temperature and, super closely controlled power supply voltages. There was just all this forgiveness by taking the binary approach. So, now analog computers are sort of long gone, and they've been completely supplanted by digital technology. So one of the simplest, most basic components of digital logic is called an inverter. And I want to explain, here's where we wish we had GoToMeeting, but we're in a podcast, an audio format. So I'm going to need people to sort
visualize here.
Yeah, if you're driving,
proving my point.
Exactly. If you're driving while you're listening to this, do not close your eyes. But anybody else, I'm going to draw a picture for you. We have to do a little bit of schematic work with electricity and early electronics to explain the principles. But when I'm done, I think everyone's going to get a kick out of what they understand. I'm going to simplify things a little bit here and there, but fundamentally, this is the way all of this stuff began to work. If we imagine in this visual slate that there's a wire running along the top, which carries a voltage, and another wire running along the bottom, which is the ground. So that, and this is the way most of these logic diagram schematics are drawn, is you'll have sort of a bus running across the top that has a voltage, which is just a pressure essentially created by a power supply, and anchored at the bottom is another wire, sort of a bus running horizontally, that is the ground. You then you interconnect things in between this positive power supply potential at the top and the ground at the bottom. If we had two resistors, a resistor is a component with two wires coming out of each end, which, as the name sounds, resists the flow of current through it. Essentially what it does is you run current through it and it gets hot. It dissipates current in the form of heat. So imagine in this circuit diagram that we have two resistors connected, the first one at the top coming down to the second one, which then connects to the ground at the bottom. So that we have a circuit formed just with two resistors in series. And for the sake of simplicity, we'll assume that they have the same amount of resistance. Well, this forms something called a voltage divider, because essentially when we make this circuit with just two resistors in series, voltage will flow through this circuit. And the direction of voltage flow is sort of controversial. I can't remember now. I was trying to remember which direction I learned in high school. Some people think of voltage flowing from the negative to the positive. Some people think of it from the positive to the negative. It really doesn't matter. Technically, one direction is current flow. The other is the flow of the electrons, which sort of goes in the, being negative, goes in the other direction. So either way, all you have to have is a consistent system, since it's really a sort of an arbitrary designation which way the current is flowing. So we have this, what's called a voltage divider. So at the very top is our power supply voltage. What happens is the resistors share this voltage drop, as it's called, between the positive power supply voltage and ground, so that the junction where they're connected in the middle will be at half of that power supply voltage, because they evenly divide it. And so that's sort of the first thing to see, is you have two resistors connected together. They form what's called a voltage divider, and the voltage in the middle, or the voltage at their junction where they're connected, is half of the total voltage. So now we take out the bottom resistor and we replace it with a switch, just a standard mechanical switch. It's got two wires, and depending upon whether the switch is open or closed, open means they're not connected, closed means they are. If we close the switch, then the switch is essentially a short circuit. So now that resistor that's still on the upper half of this little circuit, its lower lead is connected through the closed switch to ground. So its lower lead is now at 0 voltage at ground when this switch is closed. If we open the switch, then we've disconnected the circuit, and the lower lead is now it now has the same voltage as the power supply because there's no current flowing through this resistor. There's no voltage drop across the resistor. So now we go to the next step and we replace the switch with a transistor. A transistor is a 3-lead device, a 3-terminal electronic device. We've all heard of transistors, of course. The way it works is it works like an electronic switch. We put this transistor in the circuit, and so the transistor has an input on what's called the base lead of the transistor, such that when we put a positive voltage on that base lead, on the input of the transistor, the switch closes. That is, the transistor sort of works like the switch that we just took out, but it's controlled with the voltage on its base. Actually, voltage and current get complicated here, and I want to keep this sort of simple so we can stay to what's important. But the idea is that if we put a positive voltage on the base of the transistor, that is the input of the transistor, some current will flow through the base, which turns the transistor on. But remember that when the transistor's on, it pulls the lower end of that resistor that's coming down from the supply voltage, it pulls it down to ground, that is down to 0. So what we have is an inverter, because when we put a positive voltage on the input of the transistor, it turns on, which pulls that junction between the resistor and the transistor down to 0. So a 1 goes in and a 0 comes out. And if we move the voltage on the base of this transistor, the input of the transistor, down to ground, then the transistor turns off. And with the transistor off, then that junction between the resistor and the transistor goes up to the power supply voltage. In other words, a 1. So what we have is this with just 2 components, this resistor that goes up to the positive power supply with a transistor hooked to it going down to ground. We have an input into the transistor, and the output is that junction between the resistor and the transistor, and that creates an inverter. So we have, with these 2 components, one of probably the most basic logic system that you can have. So that's an inverter. It's certainly useful by itself, but we can do something, make a one additional change to it to begin to create some logic gates. And that is, we take another transistor and hook it to the same place. That is, we put these 2 transistors in parallel with each other. Another transistor hooked to the same place so that either of them are able to be turned on and pull this output down to ground. That is, hook the bottom of the resistor down to ground. So now, look what we have. If we turn either transistor on by putting a 1, binary 1, into either of the inputs, then that transistor will turn on and pull the output down to ground. And they can both be turned on. We get the same result. So what we have is in logical terms, is called a NOR gate, which NOR stands for not or. So if either input is a 1, the output is a 0. So we have the beginning of logic. Now, we know how an inverter works. The inverter was just the transistor and the resistor. So we could take one of those and hook it to the output of this little NOR gate, and that would invert its output, turning it into an OR gate. So now if either of the inputs is high, the output of the first part is low, and then that's inverted so that the output of the final thing is high. So if either input is high, the output of our little OR gate, composed of this NOR followed by an inverter, is high. We have an OR gate. Or conversely, we go back to this NOR gate, where either input is high and the output is low. If we put inverters on the inputs, on each input, then look what we have. If we just with the NOR itself, if either input is high, the output is low. Well, the other way of saying it is only if both inputs are low is the output high. So if we invert the inputs, then only if both inputs are high will the output be high, which is an AND gate. So we could have two inverters that feed into the NOR gate, and we end up with an AND gate. So it's possible just with this, using simple components of transistors and resistors, and this is actually a family of logic called RTL. RTL stood for resistor transistor logic, and circuits that were exactly like this were very popular, and this is the way digital logic was originally created. So it's clear that by assembling these little building blocks in different configurations, we're able to create sort of fundamental logical connections. Now, one of the core things that a computer has is registers. It needs to somehow hold data that it's working on. We need to be able to, for example, load data from memory into something called a register, or an accumulator. Well, what is that? How do we go from having and OR things that which we know now how to build? How do we have memory? How do we store something? Well, there's an interesting trick, and it would be fun to know who actually was the first person to come up with this, because it's clever. And that is, we've seen how we create an inverter where we just have a resistor coming down from the power supply to a transistor, such that if we put a 1 in, we get a 0 out. Well, if we connect another inverter to the output of the first one, and then connect the output of that second inverter back into the first one. So we have two inverters that are connected in a chain or in a ring. Look what happens. If we have a 1 input going into the first inverter, we know that it gives us a 0 out. Well, that 0 goes into the second inverter, giving us a 1 out, which we feed back into the first inverter. So it's stable. That is, it just sits there like that. And it'll sit there forever like that. But if something were to briefly, for example, pull the input of that first inverter, which is a 1, pull it down to ground to 0, well, then its output would go to 1. So the input to the second inverter, which would now be 1, it turns into a 0, which it feeds back into the beginning, and that will be stable. So whatever state these two inverters are in, they stay in. And that's the basis for another fundamental logical thing called a flip-flop, because it flips or flops in either direction, and it stays that way. Now, when I talked about like if something pulled that input down, that the way this is actually implemented is with something like a NOR gate. So if this circuit gets a little bit more complicated, I'm about to sort of start waving my arms around and not going into the same level of detail as we pull back from this. But if we, instead of hooking these inverters to each other, we hooked our NOR gates to each other, then imagine that both. So the circuit is, we have a NOR gate. We have two NOR gates. The output of the first one goes to one of the inputs of the second one. The output of that second NOR gate goes to one of the two inputs of the first one. So we still have the notion of these things being connected to each other in a ring. But now we have each of those NOR gates has the other input, which is not participating in this circular interconnection. And that's actually where we're able to briefly change one, briefly like put a pulse on one, to flip this flip-flop from one state to the other. And that's the basis for a register bit. Now, we want to do other things like add bits together, add numbers. It turns out that addition of a binary number is essentially synthesizable just from these fundamental logic blocks. And we've sort of talked about this a few weeks ago, where if you look at adding two bits together, they are, if both are 0, the result is 0. If either one is a 1, then the result is 1. If they're both 1, then the result is 0 with a carry. And so binary math works exactly the same as for example, the decimal base 10 math that we're used to, where, for example, if you had 5, you're adding 5 and 0, you'd get 5. If you add 5 and 5, you get 10, meaning that the units is 0, and we've carried a 1 into the tens position. Well, binary works the same way, where if we have two 1s, the result is 0, and we carry the 1 into the next position. So it's possible to express that logic with just the gates that we've seen designed here. There's what I just described is known as, in logical terms, as a half adder, because it's able to take two binary bits and produce a result with a carry. Now, the tricky part is the next bit over, the next highest bit, it needs to be able to add its 2 bits, but also accept the carry from the position to the right, the one less significant bit. That's a little more complex nest of logic, which is called a full adder, because it's able to take 2 inputs and the possibility of the carry from the prior result and incorporate that into its output and also send a carry to the next one. So essentially, by stacking enough of these full adders together and interconnecting them so that the carry out of one goes into the carry in of the next, and the carry out from that goes into the carry in of the next, you're able to take 2 binary numbers, and after this thing settles down, there's like a ripple effect. If you imagine that you put the two numbers in, well, the result of the first two will produce a carry that goes into the second two, and that may produce a carry that goes into the third two, and so forth. So this carry ripples down through these full adders to produce a result, and then the final stage of this full adder, it produces a carry, which in computers is often called the overflow bit, because the idea is if we were adding 16-bit numbers together, the result of adding 16-bit numbers could be a 17-bit result. That is a number that would not fit in 16 bits. That's exactly the same as in decimal. If we're adding like single decimal digits, well, we know that a single digit can hold up to 9, so we could be adding any two decimal digits that sum up to 9. But if we try to add 7 and 7, well, we know that that's 14. Well, that 14 won't fit in a single digit. It needs 2. Similarly, it's possible to add two binary numbers where the result won't fit in the same size as the binary numbers. So you have that's what happens with that final carry bit that overflows outwards. So that's sort of the fundamental architecture for the way bits are managed in a computer.
Do you think that people figured that out a priori? I guess Alan Turing did all this long before hardware was available to do it in his head, and maybe even going back to Ada Lovelace, right? I mean,
well,
of course, we didn't have this binary thing until we knew it was going to be a switch.
Right. That's a very good point. And all of this can be expressed mathematically rather than electrically.
It's got a Boolean logic, right? I mean,
exactly. Yeah. Boolean algebra, Boolean logic allows you to do all of this kind of stuff and work out these problems.
And that's well known. I remember studying that in college before there were personal computers. And, it's fun. You do it all on paper, and you have and, or, not. I can't remember if you have things like NAND and NOR, but you learn all those, and there's even symbols for all of that. So It makes sense that then if you give somebody some hardware, you say, well, okay, you have a switch, and you have inverters and all that stuff. Now, how do you duplicate those functions in this hardware? And that's really what you're talking about.
Exactly. And at the time, now if we think about the cross-connected inverters with some additional logic around them, one of the things, which basically forms a storage register, and then you want the ability to load them with a value that's coming in on a set of signal lines for however many bits. Well, that's going to take, maybe call it 20 transistors and some resistors. So that's for like 1 bit of NOR gates cross-connected with some other gates to gate their inputs. So that's maybe 20 transistors. Well, back in 1960, a transistor cost a couple dollars. I mean, like one transistor was a couple dollars. And it was a little silver can, smaller than a dime, sort of like a pencil eraser. Think of it like, the end of a regular pencil eraser, sort of like that with 3 leads. So it's a couple dollars. We'll say that the resistors that are also going to be scattered all over the place are free. We'll just toss them in because they were always pretty inexpensive. But 20 transistors at $2 each is $40 for the logic to implement 1 bit of a register. So that's just like raw cost. That's not even burdened with, all the other costs. The other thing then you have is the need to interconnect all of these, because you've got 20 of these little eraser head things with 3 wires and a bunch of resistors. Now they have to physically live somewhere on a circuit board. And that's got to have interconnections, which are, traces on a circuit board, but now you've got to interconnect them into a family of these. So you need connectors to allow this little circuit board that represents, remember, just one bit of storage forming one bit of a register. You got to be able to plug that into some sort of a backplane where wires then go from one to the other to connect them into a multi-bit conglomeration. So maybe this is $50 by the time you're done for this one-bit register, and you want to do a 20. You want 20 bits of binary resolution. So now you've got $1,000 that you've spent for 20 binary bits of storage. That's all this is just, it can store a 20-bit value, but you haven't been able to do anything else with it yet, and you spent $1,000. So, and that's not profit. That's not $1,000 of sale price. That's $1,000 of cost, including something for the interconnection. So from the beginning, the engineers who were trying to design a computer that could do something useful, they were designing them with these individual switches called transistors and resistors that sort of go along with them, at a cost that meant that literally every single bit that they used was expensive, and they were trying to bring the costs down as quickly as they could, as far as they could, to make these computers much more accessible to people. What I want to do next week, since we sort of understand this, is take a look then at the next stage, which is, what do you do when you've got memory and you've got a register like this? How do you turn this thing into something that can get some work done? And that's what we'll do in 2 weeks.
I love it. It's so interesting to think, what you said, $1,000 for 20 transistors, something
20
like
bits.
20 bits.
One 20-bit register.
And now we've got, somebody pointed out in the chat room, we've got, NVIDIA GT200 cards, which cost about $100, $200 for, get ready, 1.4 billion transistors. Billion! Billion! That's amazing, isn't it? But it was a huge insight to say we can do this. And then that began, with Moore's Law behind it, that began the amazing revolution that we've seen today.
I read a really interesting book last summer about the invention of the integrated circuit, and the breakthrough. It was actually, there were some people in Texas at Texas Instruments and also at Fairchild in California, and there was some argument about who actually got it first.
Right.
But at about the same time, there was parallel invention, because what happened was everybody was running up against what they called the interconnection problem. It's like, we are dreaming big. We're ready to do more. But what happened was just the physical need to interconnect the pieces. That became the limiting factor. The individual components were so big, and that they physically took up so much room that you needed to lay out the space. And before long, it got too big to run wires all around it. And so the interconnection problem was what the integrated circuit solved when it was able to say, hey, they even knew they could make resistors out of silicon. They could make diodes. They could make transistors. The fundamental pieces they knew how to synthesize, but they didn't know how to, even on silicon, how to interconnect them. That breakthrough then, opened the floodgates.
It's amazing. Eden in our chat room sent me a link to the Wikipedia article on transistor count, which has a remarkable graph that shows how rock solid Moore's law is. It's a logarithmic chart that starts in 1971 with the 4004, which had 2,300 transistors. Essentially, transistors is a switch, right, Steve?
Yes, and exactly as we just covered. It is just like it replaces a switch.
So it's 2,000 switches. Going up to 2008, where a 2 billion switch quad-core Itanium. But look how straight that line is. If you go to this curve, and because it's a logarithmic scale, that means doubling. Incredible. I mean, it's one of the most remarkable predictions of all time because it's held true for almost 40 years. And I mean, true. I mean, right on true.
Yeah.
Almost self-inflicting because in fact, Gordon Moore was the chairman of Intel. So maybe they said, well, we have to do this. I don't know. But amazing. Just amazing. Really remarkable. What an age we live in. And it all starts where we just started. Well,
and what is so remarkable, and this is what we'll look at in 2 weeks, is I hope to be able to demonstrate with such crude tools, with something so simple as a really basic computer, it is possible to do an amazing amount. Again, as we said at the beginning, like a dumb box of rocks, but really fast rocks.
Really fast rocks. Hey, we're gonna next week do questions and answers as we always do on the Modulo 2 shows. So send your comments, your thoughts, your suggestions, not just about this topic, but also anything having to do with security to Steve via his website, grc.com/feedback. That's where the form is, grc.com/feedback. And we'll pick 10 or so questions, and Steve will answer them next week. Don't forget, you can go to grc.com for many other reasons. Of course, SpinRite, the world's best hard drive recovery and maintenance utility. It's just a must-have if you've got a hard drive. But also all the free stuff Steve does, and he does so much great stuff like Shields Up and the Perfect Paper passwords, his DNS benchmark tool. It's all there, including show notes. For this show, all of our 233 episodes, transcriptions, and audio too. In fact, 16 kilobit version for the bandwidth impaired. It's at grc.com.
So we will pick up where we left off in 2 weeks with the design of a computer.
Great subject. We'll see you next week on Security Now.
Security Now.
But enough about that. Let's get to machine language.
Okay.
Where do we start?
Well, 2 weeks ago, we sort of laid down the foundation by demystifying and OR and NAND gates and how you could cross-connect two inverters that would create a little memory cell, which could remember if it was set to 1 or set to 0, a so-called flip-flop. And I wanted to convey to people the sense from back in 1960, essentially, for the number of components that were required to do even the simplest things. So now we have gates and the ability to create a register of individual bits which can be read and written. So how do we make a computer? And I know from talking to people so much, there's sort of this mystique about assembly language and machine language as if like you have to be some galactic guru in order to understand that. It's like, oh, that's like really, deep voodoo. And, I'm going to use C or Perl or PHP or Python or something. The truth is that what's actually happening down at the hardware level is really simple. And I mean, I'm going to demonstrate that now by looking at and sort of developing right now with our listeners a completely workable, usable computer using only what we understand, no magic. And I believe that once we've gone through this exercise, sort of wiping the slate clean and just saying, okay, let me just think about this, people are going to end up thinking, well, okay, that's it. And the answer is yes. I mean, it's not that big a deal. So we have memory for any machine. Back in the early 60s, we had gone from drum memory to core memory. Drum memory was sort of the predecessor to core, the idea being that you'd have a magnetized drum that was spinning and literally use the impulses coming off of the drum as the contents of the computer's memory. Thank goodness that was replaced when this concept of cores, little tiny donuts essentially, that are magnetizable in either a clockwise or counterclockwise direction. We've talked about it once before. The idea being that this memory could store a 1 or a 0 based on whether the individual little donut was magnetized in one direction or the other. And you could tell which direction it was magnetized in by forcing them, like a set of them, all to 0. If they were already at 0, nothing would happen. If they had been at 1, then the act of switching their direction would induce a pulse in a so-called sense wire, and that would tell you that, we just moved that one from 1 to 0. Well, that was called a destructive read because the act of reading the contents destroyed the contents. We wrote zeros to everything, getting pulses out of those ones that switched from 1 to 0, which meant that unless we wanted to leave the 0 there, we needed to rewrite the original contents in order to put it back, which is what these memories typically did. So let's imagine that we have memory, core memory, which is non-volatile, meaning that it just we can magnetize these little cores and they'll stay set that way. And we have a way of reading out the contents of a location and getting the 1s and 0 bits that are there. So the first thing we need to have is what's called the PC, the program counter, which is it's a counter which increments one at a time, reading out the contents of successive words of this memory. Now, the word length can be pretty much whatever we want. There were word lengths back in the beginning of as much as like 36 bits, sometimes even more. The early DEC machines were 18-bit word length. And people are used to thinking these days in terms of 16 bits or 8-bit bytes. We know, for example, that the Pentium machines were 32-bit machines. And, of course, we now have 64-bit systems. So these are currently there's been complexity added to what the so-called word length means, which we're going to actually talk about in 2 weeks. In 2 weeks, we're going to talk about all of the stuff that's happened since. But back in the beginning, the word length was whatever the designers wanted. Now, there was pressure on keeping it short because everything cost so much. Remember that back then, this is before integrated circuits. So a bit that you had was a bunch of circuitry that you had to pay for every time you made one of these machines. So sure, the programmers would like more bits because that allowed them to store more stuff. But the management was saying, wait a minute, we can't afford this many bits. So there was sort of a compromise. So if we look, for example, we don't really have to worry about specifically, but just sort of imagine you had 18 bits, because that's where the first machines of this era sort of landed. 18 sort of being a compromise of different pressures, cost, and capability. So we have this program counter which will address the memory sequentially, basically stepping through it. So say we start at location 0. So out comes 18 bits into a register, which we call the instruction register. And it's one of these registers made out of individual bit memories, which we talked about last week. And, they're all expensive, but we can afford 18 of them. So this instruction register holds the memory, the data that we just read out of a given location in memory. So what do we do with that? Well, there's essentially a subdivision of the bits into different purposes. And a term that probably everybody has heard is opcode, the operation code. And sort of traditionally, the opcode has been on the left of one of these long words. So, for example, in the case of this computer we're making, we'll dedicate some number of bits to the opcode. So, okay, what does that mean? What things do we want to be able to do? We want to be able to load and store memory. We want to be able to add and subtract and maybe perform some logical operations. Now, we're performing these against something called the accumulator, which is another register. We have the instruction register. Now we have an accumulator, which is sort of our scratch pad. So that's the main working register where the data moves through, where we perform these operations. So, for example, if an instruction said load a certain location into the accumulator, then the computer would transfer the data in a given location in its memory into the accumulator. And if another instruction said store that somewhere else, the computer would store whatever happened to be in the accumulator now into the location specified. So we need to be able to perform some operations on the data in this accumulator. And so this is, everything is centered around the accumulator with the rest of the rest of the hardware sort of all existing to serve the purposes and needs of this accumulator. So if we had an opcode of, say, 5 bits, well, we know how binary works. We know that each bit gives us twice as many as we had before. 5 bits means that there's 32 different combinations of 5 bits. So if we think of those as sort of as the verb of this instruction, we could have 32 different things. And in fact, the PDP-1 was an 18-bit computer that did have a 5-bit opcode. But back then, 32 verbs, 32 actions that you could specify turned out to be more than they ended up being able to use. So as the DEC mini computers evolved, in fact, with the very next one, which was the PDP-4, there was no 2 or 3. the 4 and the 7 and the 9 were, and finally the 15 were the 18-bit lineage. They dropped the opcode to 4 bits, which is where they stayed for quite a while, for many years. So 4 bits gives us 16 different verbs, 16 different things we can do. So, for example, the opcode, meaning the first 4 bits of this word, might be 0000 or 0001, 0010, and so forth. Each combination of those 4 bits would specify a different action, and just, one simple action. So absolutely one of them would be load the accumulator with something in memory. Now, where in memory? Well, that's where the rest of the bits come in.
Well, let's answer that question in a moment. When would be a good time to interrupt you? I have one more commercial I want to get in here. Would this be a good place?
Perfect.
Kind of a cliffhanger. But where?
where in memory?
Where in memory would you put that? Before we get to that, and I tell you, this is a fascinating subject. And as I said, I've programmed in machine language, but I love the construction that you're building here, so that it all makes sense in a better way. This kind of had to be this way. But let me talk a little bit about the folks from Astaro Security Gateway. This is a product that was our first advertiser on this show. In fact, our first advertiser on the Twit network, I believe. ASTARO.com. Constantly working to improve what is, in my mind, unequivocally the best security device out there. They use both open source and closed source software as appropriate to give you the best firewall in the business, of course. All the buzzword compliant, stateful packet inspection, blah, blah, blah. Intrusion detection, of course. But then they've added some really nice features that are, some of them just for convenience. For instance, OpenPGP and SMIME support for encryption and digital signing is built in. So outbound mail can all be signed if you want, or you could do it in groups. You could do it by IP address. You could do it by user. It can all be decrypted on the way in, encrypted on the way out. This is really nice. Of course, you've got the security that you need with 3 antiviruses, 2 for email and 1 for the web. So even when your users are surfing the web, they're protected because the ASG is looking at what's coming in and scanning it as it comes in. That's a high-performance, very nice device. You could take a look at it. Actually, the best thing to do is to try it in your small business so you really get a sense of it. If you go to astaro.com, you can sign up there or just call. The best thing to do, call 877, the number 4, ASTARO. ASTARO. 877-427-8276 is the number. 877-4-ASTARO. Now, if you're a non-commercial user and you're interested in Astaro, there are a number of ways you could try it for free. There's a great VMware appliance. It's one of the top VMware appliances out there. Or you just download Astaro version 7 from astaro.com/security now. And they've done something I think is so cool. They've upped the number of users. I think it's like 100 users. I can't remember what the limits are, but it's to the point where, there's really no limit on how you can use it. They ask that you do it for non-commercial purposes. They've even bundled what used to cost 79 euros a year, the subscription to the Astaro Up to Date, which, of course, everybody who's using it commercially gets. Scalability via clustering, up to 10 security gateways. I could just go on and on. It is the only unified threat management vendor to be certified as VMware ready, by the way. They've got a great management console if you have multiple ASGs. Why don't you give it a try? 877, the number 4, ASTARO, astaro.com. We thank them, as always, for being such loyal supporters of Security Now. All right, Steve, so we're building a machine language, and it really is based on kind of the architecture of the CPU, isn't it?
Well, I think what's significant, the point that's worth making is that even though I'm talking about an architecture that is 50 years old, this is still today exactly the way computers work. What I'm talking about is a simple CPU, a simple central processing unit, but that the fundamentals haven't changed at all.
Probably not even since Alan Turing imagined how a computer would work in the 40s.
Right.
This is the fundamental way a computer works.
So we've got a 16-bit word, and the left-hand 4 bits are allocated to the opcode, which leaves us 14 bits for the address, meaning that that the word is 2 parts. There's what to do, and then the second part is and what to do it with. So a 14-bit address gives us 16K words. If we think of like 10 bits is 1K, 11 is 2K, 12 bits is 4K, 13 bits is 8K, 14 bits is 16K. So the right-hand 14 bits provides the address, sort of the address argument for the opcode verb. So say that the opcode 0000 stood for load the accumulator. So when we fetch this 18 bits instruction into the instruction register, there's some logic which looks at the combination of bits in the opcode and essentially does this one simple thing that the opcode specifies, like load accumulator, if all 4 of those bits are 0. And so what that means is that that 14-bit argument is used as the address to fetch another piece of data from memory, different from the instruction. We fetch the instruction from where the program counter is pointing. Then we fetch the data from where the 14-bit argument of that instruction is pointing, and load that into the accumulator. So the opcode 0001 might be store accumulator, and then the 14 bits following it would specify where to store the accumulator. So with those 2 instructions, we have the ability of picking up data from somewhere and storing it somewhere else, moving the data from one place to another in memory. We would certainly have an instruction called add. That might be 0011. And what that would do is, and then the 14 bits that follow would specify where to go to get the data to add to what's in memory. Again, it would, and this class of instructions are collectively called memory reference instructions, because each of those opcodes references memory. It loads it, it stores it, it adds it to the accumulator, it might subtract it from the accumulator, it might AND it against the accumulator or OR it with the accumulator. Basically, very simple, simple bit manipulations against the accumulator. Now, the computer is useless to us unless it's able to have some sort of I/O, some sort of input-output. So one of those instructions, which would not be a memory reference instruction, would be an I/O instruction. Maybe that's like 1111, all the way at the other end, the 16th instruction, 1111. It would be formatted differently. That is, the memory reference instructions were all an opcode followed by 14 bits that specified where in memory to do its thing, whereas the last instruction, 1111, that's an I/O instruction. So the rest of the 14 bits might, for example, specify an I/O device. Many of the early computers had, like, you could attach up to 64 devices. Well, 64 is another power of 2, which you require 6 bits to specify. So there might be a field in those remaining 14 bits that is a 6-bit I/O device number, meaning the teletype, the mag tape, the card reader, the card punch, whatever device it was. And then some of the other bits might be start the device, stop the device, read the device, write the device, different bits that are about input-output rather than, well, because those apply to that specific instruction. So what we see is that there's always a field in the instruction word for specifying the operation, and then depending upon that operation, the remaining bits provide arguments of one form or another to it. Now, at this point, we've got a computer which is able to move through memory, incrementing its program counter once for every instruction, and reading what's there and causing something to happen. Read, load and store, input something, output something. The problem is it just goes in a straight line. And while that's certainly what you want some of the time, one of the things that computers do is make decisions. And that requires altering the normal linear incrementation to jump somewhere else. One of the way this was done then and even now was to have a skip instruction, the ability to skip over a word in memory. Even though that wasn't very powerful, it was powerful enough, because what you might have had, and certainly would have, one of our instructions, we talked about load and store and add and so forth. Well, one of those, like instruction 81000, that instruction could be the jump instruction. And so when we load the instruction in the instruction register, and the opcode is 1000, that is the left-hand 4 bits is that pattern, well, the argument to that instruction, the other 14 bits, is the address we want to jump to. So all the computer does is it loads that 14 bits into the program counter, so that instead of the program counter incrementing one at a time, we've just replaced the contents of the program counter with the 14 bits in the jump instruction, which means that the next instruction we fetch is at that location. We've just jumped our program execution to a different place. That's all there is to it. And so the way the skip comes into play is that if we tested something, like say that one of our instructions was skip if the accumulator is 0, or skip if the accumulator is not 0, that kind of thing. Well, if we were to subtract 2 items and they were the same, then, that is, if they were equal, then the result would be 0. So that allows us to determine if 2 things are equal or not. And if we had an instruction that said skip if the accumulator is 0, then the instruction it's skipping over would be a jump instruction, which is, this is all a very simple way of implementing the control of the program's flow, so that if the 2 things we were comparing were not the same, the accumulator would not be 0, so we would not skip the instruction that follows. That instruction that follows would be jump completely somewhere else. If we don't skip, then we land on that jump instruction and go completely somewhere else. If the accumulator was 0, we skip over that jump instruction. And all skipping means is, instead of adding 1 to the program counter, we add 2, or we add 1 twice, which is actually how these machines worked back then. And that just causes us to skip over a jump. So essentially, that means we can branch to anywhere we want to in memory, or continue on our way, which gives us, even though that's very simple, that gives us enough power to allow machines to make decisions. And we've got input-output, we've got math, we've got the ability to transfer data from one location in memory to another. Those are all the essentials of the way a machine functions. That is machine language. Now, the one layer of humanity that's put on top of that is what's called assembly language, which is nothing but naming things. For example, you create a sort of a so-called mnemonic for the different instructions. So, for example, load the accumulator would be LDA, store the accumulator STA. You want them to be short because you're going to be typing them a lot. Remember that, you end up using lots of little instructions in order to get something done. And then the only other thing really that assembly language does, it allows you to name locations in memory. So, for example, you might say LDA for load accumulator, current score. And current score would simply refer to a like a variable, essentially, a location in memory that you had labeled current score. And then if you did STA, store accumulator, new score, well, it would first load the current score into the accumulator and then store that into a different location called new store or new score. So really that's all we're talking about is some simple abbreviations for helping sort of remember and use these individual instructions and convenient labels for locations in memory so that you're not having to remember, that's in location 329627. I mean, who can do that? So instead, you label that location with an English an alphanumeric phrase of some sort, and then you refer to that location by the phrase rather than by its actual number. And in fact, you don't care what the number is. That's one of the things that the assembler will do for you is you just say, I need memory called these things, and it worries about where they go because it doesn't really matter to you as long as they're consistently referred to. And that's the whole process. That's machine language and assembly language. And that's the way it was 50 years ago, and more or less that's the way it is now.
Very cool. It's amazing, really.
And it is. We referred to it the other day as a dumb box of rocks that was just very fast.
Exactly. And this is what's. I think that was the most valuable thing about me learning how assembler works is you see every individual thing it does. And so you see exactly that. That's the lesson is it's not doing very much. It's just doing it fast.
It's why I like it because nothing is hidden.
Right.
That is, there's nothing going on underneath that. One of the problems that I see programmers having is they assume that the compiler, like a C programmer, is expressing much more abstract things. For example, when you're dealing at the machine level, you are truly dealing with fixed numbers of bits that you're moving around under your command. When you abstract that a lot, you're now talking about sort of, like double precision something. And but the details matter. And it's where the programmer assumes that something is going to be done for him or her by the compiler that the compiler doesn't agree with. The compiler says, no, that's not what you told me to do. I'm going to go off and do this. So that kind of miscommunication in assumptions is where a lot of problems crop up. And for me, by insisting on actually doing the individual small little bite-sized pieces, there's no room for argument.
Yeah.
I mean, when I make a mistake, it's mine. It's because I told the computer, move this chunk of bits over here, and that was the wrong place to go. It's not that I told it something and it did something different.
Yeah. Well, doesn't mean there are no bugs or surprises. I mean, because humans may think they're saying one thing and the computer think another, but it's much less ambiguous.
Yeah.
I mean, it's pretty clear. And I would guess there's kind of fewer interactions. Although I don't know about you, but as I used assembler, I built larger and larger macros that, in effect, represented higher level commands. You must do that, right? You're not going to write out each little thing every single time.
Well, we're going to talk. One of the things we're going to talk about in 2 weeks is the nature of indirection and pointers.
Oh boy, that's fun.
And
oh boy, if you there are two things I found very difficult to learn in programming. Indirection was one, and recursion was the other.
It's hard. It requires you being very clear about whether you mean something or the thing that
right.
thing points to.
I remember very well. Now it's obvious to me, but I do remember very well when I first started writing in C, learning where to put that little caret and where not to. Oh, this will be fun.
Yeah,
this will be fun. Oh, I'm really enjoying this, Steve, and it's bringing back memories. It makes me want to drag out my copy of MSM.
Well, and I mean, what we just described, that is what I described is a working computer that has everything it needs to get something done. And I think the mystery or the surprise is that just that. That's all our computers do. They load and store and perform simple operations on little bits of data. And look what we get as a result, because because there's enough of these little bits of data, and it's able to do stuff so fast that they perform, magic, really.
Very awesome. Steve Gibson, you the man. Thank you very much for this show and everything you do. If you are at all interested in more of Steve, you can get all the Steve you want at grc.com. That's the Gibson Research Corporation, grc.com. That's where SpinRite lives. You might as well just run over there and get one right now. You're going to need it someday. If you've got a hard drive, you need SpinRite, the world's best, frankly, only decent hard drive recovery and maintenance utility. grc.com. While you're there, check out this show's notes, transcriptions, 16 kilobit versions for the bandwidth impaired. Steve's got great show notes. We have some visitors in the studio, Steve, what's your name? Alex was saying that as a student, a computer science student, we had an assignment to talk about web security, and he went to the show notes and he got the transcriptions, and he says the only thing that really helped me understand it so I could write this paper. So you really provide a real service. grc.com. You can watch the show. We do it live every Wednesday at 2 p.m. Pacific, 2 p.m. Eastern, 11 a.m. Pacific. That's 1800 UTC at live.twit.tv. And, of course, iTunes and the Zune store and all the Winamp. Everybody has a subscription to this podcast, but you can find it directly at twit.tv/SN. There's a little subscription drop down there, and you can pick your poison. grc.com for Steve's site, twit.tv/SN for ours. Steve, we'll see you next week.
Talk to you then, Leo. Thanks.
Security Now.
Love it. All right, Steve, I'm ready to become indirect. I think that was an apt description of a pointer.
Yeah, it was a high-level pointer.
Very high level.
It was a very high level.
All right, I'll let you do the low level.
That's sort of like go north, young man.
Okay. Well, that's an old Zen proverb,
I guess it was west.
That you go west, but you point at the moon and
I'm already west, so I can't go much further west. I get west.
You get west. You point at the moon, and they're looking at the finger instead of the moon. Babies do that. You go look at the moon. They don't get that the finger is a pointer.
Ah, true. That's indirection.
Yep.
Okay, so if we turn back 2 weeks to where we talked about machine language, we'll remember and recall from that we have a bunch of memory, which is organized in words, which contain each word containing a set of bits, and that a program counter is used to address a particular word in main memory, which it reads from memory. The bits then determine what the machine does in that step, and everything is done sort of step by step. So, for example, in the machine, the little virtual machine we designed 2 weeks ago, the upper 4 bits were our opcode, and they would that would give us one of 16 different possible operations. And so, for example, if it was 0000, if those the leftmost 4 bits were all zeros, that might be the add instruction. And the balance of the bits in the word would be sort of where the opcode is the verb, the balance of the bits would be the noun. That is, add what? That is to say, add the contents of a certain location where those bits in the word would specify the address. Or we might load from a location, or store to a location, or and the contents of the accumulator, which is sort of our scratch pad storage, with a certain location. So once doing that, the program counter would increment to the next word in memory and do whatever that said, whatever the opcode in that word specified. And so if you really think about it, it's a script. This program is a script of step-by-step instructions which the computer executes. And it gets a little more complicated because it's able to step out of sequence using skip and jump instructions to go somewhere else. So there's our computer. Now, imagine a problem, as the designers of this early computer and all early computers did, where, for example, we have a document that's living in the computer's memory, and we want to search it for a certain word, which, and we use find in our word processors all the time. The idea being that the computer needs to scan down through memory, through this document, to find what we've told it we want it to locate. So with this simple computer that we've got, how do we specify a succession of different addresses in memory? That is, the word contains the address we want to load, but it just contains that one address. It doesn't, how do we scan through memory? Well, if we only had what we've described so far, there would be 2 ways to do this. You could have individual instructions, one after the other, that loaded successive locations in memory into the accumulator to see whether it had what we were looking for. That is, an instruction would be load location 100, and then it would check to see, then it would be load location 101, and it would check to see, and load location 102. Well, obviously that's a hugely long program because you're needing several instructions in order to check each location in memory. So that's arduous. Now, the other approach would be something that is generally frowned on, and that is self-modifying code. That is to say, since the instruction itself is in memory, and for example, it said load location 100, then the program could change that the actual data for that instruction from 100 to 101, and then load it, see if we found it. If not, then increment that location of the actual specified in the program to 102. So the problem is that it requires that the program is modifying itself, which becomes messy pretty quickly. So what the original architects of these early machines decided is, instead of the instruction, like said, load 100, instead of that instruction specifying what to load, the instruction would have an option of specifying the location that contains the address of what to load. Okay, so and it's we have to be careful even by the way we talk about this, because it's amazing how easy it is to get tangled up. But in these early instruction sets, as I talked about it so far, we had, for example, a 4-bit opcode, and the rest of the bits specified what the opcode acted on, what address in memory was loaded or stored or added or whatever. These early computers used one more bit. That is, so there was an opcode of 4 bits, and then, for example, another bit right next to it called the indirection bit. And then the rest of the bits that were remaining specified the location. That is to say that the designers of these machines took one more bit for this purpose from the instruction. So what this meant was, if it was a so-called, for example, an indirect load, if it said load indirect 100, what that meant was the computer would get the contents of location 100 and treat the contents as the address to load the data. In other words, that the location, the contents of location 100 was a pointer to the data that should be loaded. And that is a incredibly powerful concept. It
seems so simple.
Well, yes. And the reason it is simple, and it was even simple to do in hardware. I mean, all they had to do was, they were going to load the contents of 100 anyway. So they did. They loaded the contents of location 100, for example. But the question is, do you use what you just loaded, or do you treat it as the pointer to what you want to load? That's so the logic in the computer was, it was inexpensive for them to implement this, and they got something so powerful as a result. So if we return to our simple example of searching memory, all we need to do now is the program refers to to location 100, but we're using the value of that as the address of the data that we're going to load. So we simply increment that location. And in fact, the early machines like the PDP-8 and the PDP-11 and even the Data General Novas, it was another machine of that time, they had what was called auto-incrementing memory. That is, auto-incrementing locations. Literally, a reserved block of memory, typically down at the beginning of memory. In the case of the Data General Nova, it was location, I think it was 7, 8, I'm trying to think of which location. I don't remember now. I think it might have been octal 10 through octal 17.
It's so funny that you remember it.
so it was the 8th through the 15th locations. And the way that worked was, if ever you referred to those locations indirectly, the computer itself would increment the value for you. And what was really neat, remember we talked 2 weeks ago about this notion of memory which destroys its contents when you read it, like core memory, which is what was used back then. In order to read the contents of the memory, you needed to destroy what was there. Essentially, you wrote all zeros into the memory word. And the inductive pulse caused by the cores switching from 1 to 0 is what let the computer know what had been stored there. But in the process, you wrote zeros. So it was necessary to have a second memory cycle to write back what you had just destroyed. But in the case of auto-incrementing, you wanted to write back one greater. So what was so clever is that you sort of got this auto-increment or auto-decrement for free. That is, it sort of folded it right into the recovery of the prior contents of the core memory, so that, again, very simple logic to just increment the value by 1. We talked about that last week in one of our Q&A questions about how do you increment something, and it's very simple logic to do. So now with this very bare bones instruction set, we're able to easily scan through as much memory as we want to. We simply say, instead of using location 100, for example, on a PDP-8 or even in the early Data General Nova, the Nova also had auto decrement a block of memory, and when you referred to it indirectly, the computer would decrement, so that you're able to sort of scan from high memory down as opposed to low memory up. So in the case of our little project here to locate something in memory, we would establish the beginning of the buffer that we want to scan. We would put its address into, say, location octal 10. Then we would say load indirect 10. So we're not loading the contents of 10. The computer reads the contents of location 10 and increments it and puts one more than that back in 10. Then it uses the value that it read from location 10 as the address as the address containing the data to be loaded. And so our program can be very small, very efficient, and every time it does this load indirect octal 10, it gets what actually is loaded is a word somewhere else in memory, and it's the successively next word every time we do this. So again, very simple, tiny steps, but very powerful. Now, what we've done is to empower the programmer with a concept which is needed for the sake of programming efficiency, but it's tricky because even today, we're talking about security problems all the time that contemporary software has. And Leo, you were talking about, you've done programming.
Yeah.
And for example, in C the pointers are used.
It's built into the language.
It's exactly. It's intrinsic property of the language. And in fact, pointers have historically caused so much problem that there are languages that boast they don't have them, because it's like, oh, if you don't have this, you can't get yourself in trouble. And what happens is programmers can easily make the mistake of whether they are referring to something or they're referring to where that something points to. And it's funny. I think the problem is there isn't a good analogy in life. That is, we're used to seeing something and you reach out and grab it, and there's no indirection most of the time. And so I don't think mentally we humans model something as abstract as a pointer. I mean, we understand intellectually what it is, but in the years I've been programming, I'm always having to be very careful, and programmers who have used pointers extensively know they have to be very careful to make sure that there isn't a gap between what they mean and what they tell the computer, because the computer, as we know, is very literal. It'll do exactly what you tell it. So one of the for example, in C or any of these pointer-based languages, you need to be able to get the address of an object as opposed to the contents of the object. And if you think about it, if you had a language, say like BASIC, the basic language, until you had, for example, peek and poke, as you were referring to, Leo.
Yeah. That's indirection in a way, right? Because you can.
Oh, it absolutely is. Yeah. If you just have the basic language where you say, A equals 1, B equals 2, C equals A plus B, you cannot get yourself in trouble. I mean, there's no notion of pointing to something else. A and B are variables. The language takes care of that for you. If you say C equals A plus B, then again, the compiler is completely hiding that.
Right.
But as soon as you say A equals where B is pointing to, now, I mean, you have let the genie out of the bottle, because as a pointer, that B, where B is pointing to, it can point to anything. I mean, it can point to outer space. It can point to the operating system. It can point, to data structures inside the program. I mean, suddenly there is an awesome amount of responsibility that comes with that power. And frankly, it's one of the things that makes C that allows people to regard C as a relatively low-level language. It was designed from the beginning to be a language close to the machine in which you could implement system-level software. Unix was written in C.
Yeah. Huge.
And so it's an intrinsic of machine language. It's always been there. One of the variations as we evolved is the notion of what was called index registers. You could, or indexing, which is just another way of saying the same thing, where you could, in some of the early machines that had, for example, like the Data General Nova, had 4 accumulators, AC0, 1, 2, and 3. And the last 2 accumulators, AC2 and 3, could be treated as so-called index registers, which is exactly what we're talking about. We're saying that they contain the address of the target location rather than their contents being used directly. And index registers are a component, and indirection is a component of all contemporary machines today. They come in different shapes and sizes and an additional complexity, but this basic structure has been around from the beginning and is really powerful.
Indirection. Next, recursion. You're gonna, I mean, I tell you, pointers was hard for me, even though I had, as I said, had experience with peek and poke. The little caret and the little ampersand and C, it was like, I use what, when, but once you get it, it is so powerful. And it's really not that hard. Now, you just did a great job in 15 minutes of explaining it.
Well, it's not hard. What I think, though, is it is mistake prone.
Okay, now the security issues arise. Yeah.
Exactly, because this is what we see. And in fact, if you remember, one of the things that the bad guys do is they are able to confuse data and instructions. The bad guys, when we talk about remote code execution exploits, the idea is that data in a GIF image or in a buffer that is moved across the internet, it is not supposed to be executable. But because of the power of pointers, literally for this reason, because of the power of pointers, it is possible for data to get confused with code and for the bad guys to leverage this power to get the data that they've provided to be executed as code. And at that point, all bets are off.
Yeah. That's why you have this feature in Windows where you can't execute code out of the data stack.
Right. DEP, data execution protection.
Right.
The idea is that there are regions of memory which a programmer can, when they're setting things up, they're able to say, okay, I intend for this buffer to be data, not executable. And that was a feature added relatively recently to, in the case of Intel, to the Intel architecture, so that blocks of memory that were being allocated by the operating system could be marked as read-only, writable, or executable. or not in the case of leaving this bit off. So that literally, if your program attempted to jump, that is, again, we have a program counter in today's processors just like we did back then. So if your program counter attempted to be set to the address of an address inside this block of memory, there are gates in the chip which check the privilege bits associated with this allocation of memory and say, oh, wait a minute, the execute bit is off on this block of memory. We cannot execute from this memory. Therefore, the program counter is not allowed to fetch from that. And what that does is it pulls an exception, essentially a violation deliberately, that returns control to the operating system saying, whoops, this program just tried to do something it should not try to do. We don't know why. We don't know that it's a bad guy. It could just be a mistake in the code. But,
well, it could be intentional.
And
programmers do this all the time. They stick program code on the stack, which is, as we now know, bad.
Yes. And in fact, Windows depended upon that
right.
in the old days. It actually back before hardware graphics acceleration, where you were wanting to move rectangles of data around from one place to another on the screen, it was too slow if you had a general purpose chunk of code that would say move this many bits and then and is counting down the bits as you move them, and then goes back over and does another line, and so it like does line by line in a raster scan order. The problem was that was just too slow. So what Windows did was, when you said, I want to move a rectangle of data from one place on the screen somewhere else, it actually wrote custom code on the stack in order to do just that one operation one time, and which much faster than you could execute a much more general piece of code to do that, and then it would just discard it. And in fact, we're going to be talking about what is a stack week after next, because it's one of the next.
Oh, good. Oh, yay.
The next evolution of fundamental technology. That and actually, the early machines did not have a stack. The machine we've been talking about, our little hypothetical machine, there was no stack. But the introduction of that concept was another sort of crucial, critical addition to the way computers work. That it was so good, no one would do one without them these days.
Yeah. It's these little abstractions that advance computer science in big leaps, and it's wonderful when you get it, because your brain and your understanding of how this stuff works advances in a big leap too. You really feel it. You go, I get it, pointers, or I get it, stacks,
and the abstraction is fun. I
love it.
It's fun to well, in fact, it is. I think that's one of the hooks for people who love to program.
Yes.
Is that they get off on this kind of true abstract thinking. It's just great.
Absolutely. Yep. That's where the art and the joy of programming comes in. Steve, you're the best. Steve Gibson is the man in charge at the Gibson Research Corporation, grc.com. You can find Spin right there. That's his bread and butter, his day job. The world's best hard drive maintenance and recovery utility, a must-have if you've got a hard drive, grc.com. You'll also find the show there, including 16 kilobit versions, which Steve creates himself, edits with his own little razor blade and tape, and puts online so that those of you with low bandwidth can even you can hear this show. And transcriptions, which Steve pays for himself. He's a very generous guy. We don't do any of this stuff for him. He does it all on his own. Show notes and more. grc.com. If you've got feedback, next week is a Q&A episode. grc.com/feedback is a great place to go to leave a question or a comment or a suggestion.
Yep, please do.
Yeah. I think that's. I forgot. There's so much great free stuff there too. Don't worry. You don't, even if you don't have a dime, to your name, you can get great free stuff at grc.com. Steve, thank you for explaining pointers so succinctly and wonderfully. I wish I had this when I was starting out.
They are very, very powerful. They come from indirection, and like these other core technologies, they'll always be with us. And so we'll do stacks in 2 weeks.
Thank you, Steve. We'll see you next time on Security Now.
Thanks, Leo.
Security Now.
With us. So, Steve, we're ready for more in our Computer 101 series.
Yeah, we've done an hour of security news and updates and stuff. So let's talk about how computers work. This is the 4th installment, and what people will eventually recognize is that I've been very carefully and deliberately laying a foundation which I believe will end up in everyone really getting how computers function in a fundamental way. That is, demystifying this really by showing that, in my opinion, there's not that much to it. I mean, the complexity comes from refinement over time, not from the fundamentals. So in the first installment, we went to the very beginning and talked about resistors and transistors and how they could be connected to create simple logic gates and inverters, and how, for example, when you connect two inverters to each other in sort of a ring, that's an inherently stable device called a flip-flop, which forms a bit of a register which is able to be loaded and remember a binary value, 1 or 0, and you concatenate a bunch of those in order to be able to store more complex, larger values. We then, in the second installment, looked at machine language, the idea that machine language is nothing other than some form of storage which is addressable, where the address is stored in a program counter, which is just the address of the current instruction we're executing, and that the instruction itself is a collection of bits. We read a word out of memory, and the individual bits have specific assignments. Like, for example, in the instances I've been using, the top 4 might be the opcode, the operation code that says what this instruction instructs the computer to do. For example, add the contents of another location in memory specified by the rest of the bits in the instruction to an accumulator called the accumulator because it accumulates things, or store the value of the accumulator into a location in memory, or add or subtract, whatever. So it's just that simple. And then in our third installment, we looked at indirection, which is a very powerful concept. We looked at the power of pointers because in the machine language, at the machine language level, we might sacrifice one of those bits, one of the precious bits in our machine language word, to be an indirection flag. That is to say, if this bit is off, then the address specified by the rest of the bits is the address of the data that we want to load or store or add. But if that indirection bit is a 1, then that says that that location contains the address of the location to work from. That is, it's indirect. It's not a direct access, an indirect access. And the other way of saying that is that location is a pointer to the actual data. So 2 weeks ago, we looked at what that means to have pointers. So this week, I want to introduce the next major advance in the notion of how sort of the fundamentals of how computers work at the hardware level with the introduction of the concept of a stack, which uses this notion of indirection in order for it to function. We need to back up a little bit though and talk about multiple register machines, and because that sort of factors into the value of the stack. So far we've talked about a simple machine which had a single accumulator, and many of the early machines did, because the point I was early making was that all of this hardware was so expensive in the beginning. Transistors and resistors, and the space they required, the power they consumed, the problem of interconnecting them all meant that the designers had to be extremely lean with the design of their systems. So a register was a luxury to have. At the same time, it turns out that it's really convenient for a programmer to have more registers, that is, more than one accumulator. Now, remember, though, that we don't get these things for free. That is to say that bits in the instruction word, if we're going to have more than one register, bits have to be consumed in order to specify which register. So the advantage of having one was that you didn't need to specify which one because there was only one. So it was implied, there was this implication that if you're loading, well, there's only one place to load it into, and that's the accumulator. And if you're storing, there's only one place to store it from, which is the accumulator. So when machines began to have multiple accumulators, which was extremely handy to programmers, some bits of that instruction word needed to be dedicated to specifying which accumulator. So, for example, one of the early machines at the time was the family of machines from a company called Data General. There was an early competitor to DEC, Digital Equipment Corporation, called the Nova mini computers. The Nova was also one that I programmed back in the day when computers had control panels, front panels with lights and switches, and it had 4 accumulators, 4 accumulator registers, which were designated AC0 through AC3. And so the instructions in the Nova instruction set had 2 bits to specify which one of the 4 accumulators the instruction would act on. So there was load accumulator and store accumulator, but now you had 4 accumulators, not just one. So 2 bits in the instruction needed to be sort of taken away in order needed to be dedicated to that purpose for specifying which accumulator you meant. Typically that meant that you were taking bits from the rest of the word, like from the addressing range, so you were able then to address less memory with the instruction, but that was made up for by the fact that having multiple registers was so convenient. So the way the early machines handled subroutines was originally very awkward. The notion of a subroutine, probably our listeners are familiar with the concept, is that you would have some piece of code located somewhere in the computer which performs some useful function. For example, the original PDP-8 didn't have a multiply instruction. You could add and you could and you could shift, but there was no multiply. So the multiplication process, which is very useful to a computer, you had to simulate a multiplication out of the much smaller instructions. So typically what a programmer would do, and in fact, I did this on the code that I wrote for my little PDP-8 front panel toys, I wrote a multiply because the PDP-8 chip that I was using had no multiply built in. So, but I needed one. So I created a multiply subroutine where it was a series of the available instructions which had the effect of performing multiplication. Well, if I was only doing that one place in my program, then the program would execute into this multiplication operation and then continue. But say that I wanted to be able to multiply from various locations in the program. Well, were it not for having this concept of a subroutine, I would have to duplicate that multiplication code everywhere I wanted to perform a multiplication. But the cool thing about this notion of a subroutine is you could have one instance of it in memory, and you could jump to it from all the places in your program that you want, where you want to perform a multiply. The problem is getting back, because if you're going to jump to this routine from various locations in memory, different locations in your program, then once the routine, the multiply routine is done executing, it needs to know where to go back to. You can't hardwire that back to one location because you're jumping to it from different locations, and you want to return to the instruction right after you have jumped to the subroutine so that you can continue executing where you were.
Too bad there's no way to kind of store that place that we came from, just temporarily keep it somewhere.
Well, what the original designers of the PDP-8 did was they kind of came up with what we would now regard as a real kludge. They stored the location of the instruction after the subroutine call in the first word of the subroutine. And then started executing from the second word of the subroutine. That meant that the subroutine always sort of knew who had jumped to it, that is where it had been jumped to from, because that address was in its first word. So there's a perfect example of where indirection comes in. It would, when it was all through doing its work, or in this case, this multiply, it would jump indirectly through the first word of the subroutine. Since that first word contained the address that it had come from, that took it back to the place in the instruction underneath the one that had called it. So it was it was elegant from that standpoint. But it turns out that this approach has a problem. And that is, if the subroutine were doing something more complicated, like calling other code somewhere else, what if that code needed a multiply? Well, then the other code would call the multiply, and its return address, the location from which it called, would overwrite the first call of the multiply. In other words, the way to say this is that this was not recursive. You could not nest these calls.
Because you'd overwrite the first call when you did the second call.
Exactly.
You could never get back to the beginning.
Exactly. So programmers, if they knew that their code needed to be recursive, that is, if there was a chance that the work they were doing might be called, the work they were doing might cause, through any means, might cause them to be executed again before they returned, they would have to go to all kinds of extra work to, for example, save that return address at the beginning of the subroutine somewhere else, so that if they got called again, it would be safe against replacement. Well, what eventually was developed is a brilliant concept called a stack. A stack is a complete abstraction. That is, we can think of it, and people have, in describing how it worked, have talked about, for example, a stack of plates in a cafeteria. There's a buffering acronym that people may have heard: last in, first out, or first in, first out, or first in, last out, or various combinations of that. What it really is, the way to think of it in concrete terms, is there's a register called the stack pointer. So remember, we have the program counter, which is a register that points to the current instruction that we're executing. Imagine now that this computer has another register called a stack pointer, which is at the beginning of the program. Say that it just points at the very end of memory, like way, way up high at the end of the computer's memory where nothing is going on. And so essentially we'll call that all ones. 1 is the highest value of the computer's storage. So that value is put into this stack pointer register. Now, an instruction is a few instructions are used. For example, in common terminology, they would be called push and pop, where the conceptual notion is you push something onto the stack or you pop something from the stack. What pushing on the stack does is it stores the value of what you're pushing in the location pointed to by the stack pointer, and then subtracts 1 from the stack pointer. So again, we're using this powerful concept of indirection, so that the stack pointer, it's called a stack pointer because it's pointing at a location in memory. So say that we had something in an accumulator that we just needed to put somewhere safe for a while. We do what's called pushing it on the stack, which merely says we ask the computer's hardware, the processor hardware, to sort of deal with it. Here, take this. And
deal with it.
Deal with it, exactly. So what the idea is, with the stack pointer, which is pointing at the end of memory, in the beginning, we say, here, store this on the stack, push this on the stack. So that value is copied to where the stack pointer is pointing at the very last word of memory, and then the stack pointer is decremented by 1. Well, that decrementing by 1 is this concept, the concept of pushing it on the stack. Because notice, if I say, oh, now deal with this, something new has come along, deal with this. So we push this new thing on the stack, same stack, but this time the stack pointer that was decremented by 1 last time, well, it's now pointing at the second to the last word of memory. So we store this second thing that came along in the second to the last word of memory, and so on. So we're able to say, deal with it, deal with it, deal with it. And we don't really care where these things are being stored, because that housekeeping is being done by the hardware. Eventually, though, we say, hey, I need that back. And so that's called popping the value from the stack. Popping the value does the reverse. It copies the contents of where the stack pointer is pointing back to wherever we're telling it to go. Like we want to load that. If we're popping the stack into a register, it copies where the stack pointer is pointing back to our register. Well, I stepped a little bit on this. Since we store something in order to push the stack. We store something and then increment the pointer. If we pop the stack, we first decrement the pointer. So that's now pointing at the top of the stack, and then we copy where that is pointing back to our register. That sequence is important because it's got to be the exact reverse to pop as what we do when we push. But the advantage is that again, we told the computer to accept some data in a certain sequence of pushes. When we tell it we want that data back through a series of pops, it returns them in reverse order because the stack is being popped and the pointer is incrementing back towards what's called the bottom, of the back toward the bottom of the stack, back to the beginning. So we get this data in reverse sequence. So, okay, there's sort of the fundamentals. Well, now look at this in terms of subroutines, because if the computer is set up, as all computers today are, to store that return address on the stack, then this problem of recursion completely goes away. If our jump to subroutine instruction, instead of storing the address of the instruction which follows it in as the PDP-8 did at the beginning of the subroutine, it simply pushes it on the stack. That's the phrase, pushes it on the stack. Then we don't have to worry about it. The return address has been stacked, as again is the way it's referred to. We execute the subroutine, and the last instruction of the subroutine is called a return from subroutine instruction. And it does the reverse of essentially of this jump to subroutine. It removes the last thing that was put on the stack and uses that as the address to return to. So the value of this, the reason this is recursive, is that if this subroutine called some other subroutine or executed some other code which came back and called the original subroutine, that is, it would stack that address also, then now two return addresses are on the stack, one for each time the subroutine was called. And in fact, other subroutines could be called in any order, the only requirement being that they are returned from in the reverse order that they're called, which is normally the way a programmer would design things. You finish up what you're doing, and then you return from the subroutine. So the beauty of this is that the series of return instructions properly remove the addresses from the stack in the reverse order that they were stored, which is exactly what you want in order to sort of unwind yourself and get back to where you came from. So that technology is now intrinsic to the design of our computers. One of the other things that this stack is useful for is saving the state of the computer. Say that this multiply subroutine needs to use the registers which were probably being used by the person that called the subroutine. Well, it can't mess them up. It needs to leave them alone. So one of the things that this multiply subroutine could do is save those registers which it will be altering, but which it wants to be able to restore on the stack. So at the beginning of the subroutine, it'll say push register 0, push register 1, push register 2, which stores their contents on the stack. The subroutine doesn't care where the stack is, what the stack pointer is currently pointing to. It just sort of said, deal with it to the computer. Then once then it's able to use those registers any way it wants to as scratch pads, for its own work. And once it's done, it needs to put things back the way they were so that the routine which called the subroutine doesn't have things messed up. So it says pop register 2, pop register 1, pop register 0. And remember, in the reverse order that it pushed them. And so successively, the values that were stored are restored into these registers. Then it says return from the subroutine, and the stack will be pointing at that point at the proper return address, so long as the same number of registers were popped as were pushed. Because again, you need to keep these things balanced, which is some of the problems programmers get into if they're working at a low level and are not careful. You do have to be careful, because with this power comes, not surprisingly, responsibility.
A compiler will do it automatically. It's only if you're managing the stack yourself.
Well, yes, except that many of the security flaws that we have talked about are a consequence of stack overflow.
Right.
We've talked about that often. So it is possible in a powerful language like C to allocate buffers. One of the other uses of the stack, and this is where this directly impinges on security. Notice that we've been talking about pushing and popping things. Well, say that a subroutine needed some, like a buffer. It needed 256 bytes of buffer space for its own purposes, just sort of like to use for a while it's doing stuff. One of the ways a programmer could get buffer space is by manually subtracting a like 256 bytes from the stack pointer. So look what that does. Essentially, it's almost like if you had said push 256 times, you would have moved the stack pointer down in memory, coming down from the top, and you end up with this block of memory. So a programmer is able to subtract a value from the stack pointer and use that area which is above the stack pointer as their own scratch pad. Because if other things, for example, if this subroutine then pushed other values or called other subroutines, those would all be down lower in the stack. So the act of moving the stack pointer down creates a buffer. It's a nice, very fast and efficient way of allocating some memory that can be used. The problem is, look what happens if you were to ever write too much data in that buffer. Well, that would overwrite values on the stack which were above the buffer that you allocated. So that if you then popped the register values off the stack, and even more significantly, if you did a subroutine return, remember that the subroutine return's address is stored on the stack. So if a bad guy were able to cause a buffer overrun and write over any of the stack, they could put their own return address of the malicious code into the computer, and it would jump there, so that instead of returning where it was supposed to go from the subroutine, it would go into the malware. And that's exactly how much of this malware gains control over the system, just like that, by taking advantage of the stack. Powerful as it is, it does need to be treated with extreme care, because it controls the execution path of the processor.
If that's one of the reasons to turn on data execution prevention, right? Because if you can't execute code in the data area, Doesn't that prevent that kind of attack?
Yes, exactly. One of the
is the stack's considered data area.
Now it is the case that some programs will deliberately put executable code on the stack, or they will allocate other data areas and, for example, load some of themselves, like they may be a modular program where only part of the program is loaded in memory at a time. And so at some point it says, I need to go get another chunk of myself. So they'll load themselves, another piece of themselves off the hard drive into memory, which technically is data memory, and then execute that. There's nothing preventing that, except it's regarded as poor programming to do that. And so it's the kind of thing that data execution prevention would flag as an exception, which is why some benign software will not run with DEP enabled, because it'll cause that problem.
Good to know. Good to know. And some benign software wants to use the stack as a code area because it gives them some flexibility.
Exactly.
It's a kind of programmer's trick.
Exactly.
Push code on the stack.
Very handy and very efficient.
And very bad. And stop doing it. Well, now that's stacks and registers. Do you want to get into recursion today too? We got time.
I have one last thing to say.
Okay, hold on then. Hold that thought. And we'll get to that in a moment. But before we do, I do want to mention one more sponsor, and that's the folks at Carbonite, who created something just for our audience called Carbonite Pro. We are, as far as I know, the only people advertising this. This is a brand new product from Carbonite. You see, Carbonite's that backup, that online backup service we've talked about before. Very secure, uses AES 256-bit encryption. You control the keys. Uses 128-bit SSL after AES encryption to transmit. That's kind of belt and suspenders, but that's just how they like it. It, of course, gives you the chance to restore a file from almost anywhere, as long as you can get online, even your iPhone. There's a Carbonite client for the iPhone, but anywhere you can get online, you can look at Carbonite, look at your data stores, get your files. It's automatic backup, off-site. And what happened was Carbonite found out that a lot of people using Carbonite were businesses. It's a consumer product, per computer product. But the businesses found it so useful, so handy to have automatic backup that they started in steps. Several 100,000 Carbonite customers were small businesses. So Carbonite has created a product just for you, the small business, called Carbonite Pro. The same great, very secure, very effective, automatic off-site backup, but with a console that allows you to control multiple seats, a much reduced price, kind of volume pricing for it. It's just a great solution for the business. We've installed it immediately, of course. CarbonitePro.com. You could try it right now, 30 days free. I do recommend the free trial. As always, we encourage our sponsors to do that because, well, we know you're smart. We know if it fits the need, if you try it and it fills the need, then you will buy it. And if it doesn't fill the need, we don't want to sell it to you. It's that simple. CarbonitePro.com. Give it a 30-day trial. See how it works in your business. I love the couple of things I really like. The ability for the user to do a restore if you give them permission. That's nice because the truth is it's embarrassing that walk down the hall to the IT department to say I deleted that spreadsheet I'm supposed to have for today, and can you restore that? That's embarrassing. Carbonite Pro lets the user do it themselves. It has lots of nice features as the IT department, though you control it. Try it, 30 days free. CARBONITE, CarbonitePro.com. Carbonite's a great company run by great people. We were talking about David Friend, the guy who started it, former founder of the ARP synthesizer company. Just a neat guy. And I'm really proud to be associated with him. CarbonitePro.com. So I guess in a way we talked about recursion because the recursion required the stack.
Yes, I'm a little self-conscious about having made everyone's eyes cross here.
No, that was great.
But it's a crucial concept because what we're going to do in 2 weeks is discuss how computers are able to do everything at once. That is one thing we've never talked about.
Slicing.
And it's crucial is interrupts.
Yeah.
This notion of interrupts and the way that sounds can play, the mouse can move, the pointer can move, The hard drive is reading and writing. I mean, there's so much happening at once, and this concept of being able to interrupt code, which we're going to cover in 2 weeks, absolutely requires the stack in order for no matter what's going on to have its state saved. That is we talked about one instance, for example, where this subroutine, in my example, this multiply, needed to use some of the registers that there aren't an infinite number of registers. So if it was going to be modifying them, it needed to be able to save and restore them. Well, so does a system where anything could happen at any time. So I wanted to explain, both from a security standpoint, but also sort of from this fundamental architecture, how vital this concept of a stack is, how cool it is that you're able just to say, stack this, stack this, stack this, stack this, and not have any specific concern with where exactly it's been stored. One of the reasons this is so efficient, remember we talked about the notion of a register being implicit in an instruction. Well, we're not having to specify the stack pointer because that's implied by the push and pop instructions. They know how to do the work. We just sort of say to the computer, take the data. I don't care where you put it, just as long as you can give it back to me when I tell you that I want it. And the key is that it's this notion of it being we get it in the reverse direction that we gave it, allows all of this power and essentially allows this recursion because as long as we sort of unwind ourselves in the reverse direction that we wound up, we end up right back where we're supposed to be. So it works.
That's very cool. Love it. I love talking about the deep roots of computer science from a guy who was there at the beginning, frankly.
Well, there are just a couple more key concepts, and we'll have really pretty much everything we need in order to understand where we are today. Because I want to quickly, probably in the episode after we talk about interrupts, talk about today's microprocessors, the whole CISC versus RISC controversy, the issue of how many registers is enough, how Intel got itself tangled up as power continued to be consumed with the design of its processors, and the insane things that designers have done in order to squeeze every last bit of processing power out of these chips. Now that our listeners have a sense for exactly how these things run, there's enough understanding to understand very cool technology like out-of-order execution and superscalar and pipelining and the stuff that we've all got in today's processors, not just the way PDP-8s used to work.
Thank you, Steve. It's always fascinating, and we'll get more into the details of the nitty-gritty. Now, next week, though, we answer your questions. It's our Q&A episode, so if you've got a question, you can go to GRC about this or anything in the security world. Go to grc.com/feedback, and that's where you can ask questions of Steve, and we'll pick 10 or so for next week. He will. By the way, while you're at grc.com, don't forget to check out SpinRite, the world's best hard drive recovery and maintenance utility. A must-have. If you've got a hard drive, you need SpinRite. He also has a lot of good free stuff there. Shoot the Messenger, Decombobulator, Wizmo, Shields Up. I can go on and on. grc.com, and you will find 64 kilobit and 16 kilobit versions of this file, the podcast that you're listening to there, as well as the show notes and transcripts, too. It's all at grc.com. Steve, thank you for joining us. We'll see you next time on Security Now.
Thanks, Leo.
Security Now.
All right, we're talking with Steve Gibson, the security guru, the head honcho at grc.com, and we're going to continue on in Steve's series on building a computer up from scratch by solving kind of the fundamental problems that you have to solve to make a computer work.
Yeah, I don't, that famous cartoon with a professor on the blackboard who's trying to balance his equation and gets to a certain point and he, can't figure out how to make it go. And he says, and then a miracle happens. And
we're not going to have any miracles here.
Yes, I don't want at any point to just sort of wave my hands and say, oh, and just take my word for it. Or, oh, that's just kind of, happens. There is nothing that requires we do that. We've got intelligent listeners who have been paying attention. The fact is, mysterious as the inner guts of computers are, they're just not that complicated. I know it's by choice. It's where I live, programming in assembly language, because I like dealing with the truth, with the actual raw capability of the machine. And it's easy to sort of say, oh, that's just sort of beyond me. But the fact is, it's not beyond any of us. So this is the fourth in our series of sort of laying down a foundation of understanding what the exact operation, the true functioning of the computers that we're all using now in our daily lives. In the first installment, we looked at the whole concept of having a programmable machine where we had just a block of memory that was addressable word by word, and something called a program counter, which counted through the steps of the program, advancing word by word, and that these words that were read were broken down into fields of bits, where one group of bits was the so-called opcode, the operation code, which instructed how the computer would interpret the rest of the bits in the word, which, for example, might have been another address in memory, telling, for example, the computer to add the contents of that memory address into an accumulator, or subtract them, or invert them, or rotate them, or a number of different things. Maybe send them out to a peripheral device, or read something from a peripheral device into the accumulator. So you had I/O, input-output instructions, and that's really, at that level, that's all that's going on. Then in the second installment, we introduced the notion of indirection, which is a very powerful concept, the concept of a pointer, where instead of the instruction directly specifying an address from which you did some transaction, the instruction specified an address which contained the address with which you did the transaction. In other words, it was a pointer to the actual target of the operation, a very powerful concept, which we then advanced to the next stage with our third installment, which was our discussion of having multiple registers and a stack. The multiple registers gave the programmer more flexibility. He wasn't spending all of his time loading and storing things to and from memory with using a single accumulator. If he had multiple accumulators, multiple registers, then it was possible to sort of have little temporary scratch pads. He could keep things in various registers as part of the algorithm he was doing. And then we introduced the notion of a stack, which was the focus of the last episode in this series, as a hugely important and hugely powerful concept. The idea being that this was sort of a sequence-oriented storage concept, storage facility, where you could say, place a value on the stack, and then place another value on the stack, and then recover a value from the stack and recover the prior value from the stack. The idea being that as long as you put things on a stack and remove them in the reverse order, you're able to not worry about the immediate history of the stack, as long as you have some discipline about always popping, as is the jargon, popping something from the stack in the reverse order that you pushed some things on the stack, you were able to restore the contents that you had used the stack as a temporary storage to contain. Well, that's an incredibly powerful idea, because it allows us then, for example, to call to a subroutine, to jump to a subroutine to perform some work for us. And the subroutine knows that it's going to use, for example, a certain number, a certain subset maybe of the registers that's in this computer hardware, but it knows that when we call the subroutine, we don't expect it to mess up the work we're doing. We just want some service from it. So it is able to use the stack to save the contents of the registers that it might be changing, and then just before it returns to us, it restores them. It pops these values off the stack back into the registers, so that when it comes back to us, it's very much like nothing happened. I mean, we got a little work done, but if we were in the middle of doing things, then we were able to continue trusting that subroutine to clean up after itself. And that's sort of the key concept. So moving forward, we have a computer which is able to do work. You know, if we wrote some software, it could compute pi for, as long as we allowed it to work on computing pi, or do polynomials, or, do roots and cubes and, pure math computational stuff. Well, that's useful, except that computers really came into their own when they began interacting with the physical world, with so-called peripherals. We wanted them to interact with a teletype where we can type things in. We want them to be able to interact with storage facilities where they're able to not only store things in their main core memory, but sort of have a more like an archival storage to magnetic tape or to disk drives. So that comes back to this notion of input-output devices or input-output instructions where we're able to say, take the contents of an accumulator and send that out to a device. Well, in order to do that, since the computer can typically run vastly faster than the physical devices that it's using for input and output, it needs some way of pacing itself so that it's able to provide data to a device as the device is able to accept it. And it's similarly going in the other direction. It's able to wait around for new data to arrive from a device. If we take the case, for example, of a keyboard, somehow the computer needs to know when we press a key, and then to read the value of the key we pressed and accept it, store it somewhere, and then somehow be notified when we press another key. Well, the original computers did this in a very awkward way, but it was all that they really had. There was an instruction, part of the input-output instructions, which would allow them to sense the readiness of a device to receive data or the availability of data from a device. And so the computer would essentially, it would execute an instruction to read this, say that it was trying to read data from the keyboard. It would execute an instruction which would allow it to sense whether new data was available. And if so, it would branch in the program to a series of instructions that would read the data and then reset that little sensor so that it could then start waiting for the sensor to again say, oh, we've got new data available, in which case it would read that and reset the sensor and so forth. So essentially, the computer would loop like in a tight little loop, just reading the status, checking to see if that status said there was new data available, and if not, it would go back and read it again. Now the problem is the computer is completely occupied while that's happening. That is, while it's reading data, waiting for us to press keys one after the other, it can't get anything else done because it's spending all of its time sitting there just waiting for data to become available. So some early programmers said, well, we could get some work done if we sort of like went away and did some work and then checked to see if data was available, and if not, go back to kind of to what we were doing again. And so the idea would be they would take responsibility for polling the status of the keyboard every so often. Now, that was clever, and it would work in theory, but it required a great deal of discipline from the programmers who were wanting to get sort of work done on the side while being ready to accept data from the outside. Because if they got too busy, for example, just doing computational work, then the computer would seem unresponsive to the user. Or maybe two keys would get pressed one after the other, and the computer would have missed the first one. It would only see the second one when it came back, if it didn't come back often enough. So people writing code like that had to make sure that they didn't ever spend too much time not checking to see if something new was available. So the programmers complained to the hardware guys and said, okay, look, this is crazy. We can write code to keep things moving, but it's really hard to do that. There's got to be a better way. Well, what was invented was the concept of a hardware interrupt, which is an incredibly powerful and as always, when I start talking about incredibly powerful, you know that what's going to follow is and dangerous. With power comes responsibility. Like we were talking 4 weeks ago when we talked about pointers, and I said pointers are incredibly powerful, but oh boy, can they be trouble if you're not very careful with them. Similarly, hardware interrupts are very powerful, but I would not be surprised to learn that, for example, Toyota has had a problem with that kind of power because it's the way computers become asynchronous. If you didn't have any interruption, if all you were doing was running code like computing pi, then the computer is what the computer does is entirely deterministic. You start it in the morning and it starts working on pi, and 8 hours later, if you were to stop it, then it's done a certain amount of work. If the next morning you started it at the same time, if you checked on it in exactly the same length of time later in the second day, it is doing exactly the same thing. It's exactly the same place. Every single thing would have been predetermined based on its starting state. The entire future was determined by the way it started, because with simple software, it's entirely deterministic. Well, that immediately goes out the window as soon as you start interacting with the real world. What hardware interrupts allow is they allow an electrical signal of some sort, an electrical signal representing some sort of physical event like a key being pressed on the keyboard, to interrupt at any time the normal flow of instructions. So now with a hardware interrupt system in this computer that we were just talking about, the main code, the main work that's being done never has to check to see if a character is available on the keyboard. It doesn't have to explicitly check. Instead, before it gets busy doing whatever it's going to do, it sets things up so that a hardware event that occurs can interrupt it anywhere it is, literally in between instructions. So what the hardware in the computer does is, as it's stepping its program counter word by word through memory, reading each instruction in turn and doing that, some additional logic is added to the hardware, which just as it's finished executing an instruction, there's a hardware check to see if the interrupt signal is active. If not, it just proceeds as it normally would have to read the next instruction in turn and execute that. And again, after that instruction, it takes no time to do this in hardware. So there's no overhead in testing this hardware interrupt line between every instruction. It happens at light speed in the logic. The computer either moves forward, or if the hardware interrupt is active, it suspends, essentially doesn't execute the next instruction it would have in sequence. Instead, it does something different. Now, what it does in detail is a function of sort of the generation of the hardware. For example, the PDP-8, my favorite machine to use as sort of an example of in the beginning, did have hardware interrupts. And in fact, I used them in the programs I wrote for blinking the lights and playing games and things. What the PDP-8 did was, when a hardware interrupt occurred, wherever it was executing in main memory, it forced the location of that next instruction it would have executed to instead be stored in location 0 in main memory, and it changed the program counter to a 1. So what that did was, suddenly the instruction at program location 1 got executed, and the computer followed the trail from there with the exact location where it had been interrupted stored in memory location 0. Of course, that storing in 0 allowed the computer to get back to return eventually to exactly where it was. So this was a huge innovation. Suddenly, you could set things up so that, for example, when a key is pressed, no matter what you're doing at the time, suddenly where you were gets stored in location 0, and you start executing at location 1. And the formal name for that location 1 is an interrupt service routine, or an ISR, as it's abbreviated, interrupt service routine, meaning that routine, that code is going to service this interruption that the computer has just experienced. So what does it have to do? Well, we have no idea now where we were. We don't know what we were doing when we got interrupted. So now what we've introduced is non-deterministic computing, where real-time events occurring at any time change the flow of code through the computer. Well, if we want to, for example, read the data from a keyboard and store it in a buffer somewhere, we have to make sure that, almost like a physician that promises to do no harm, we have to make sure we don't change anything. That is, the computer was in the middle of work of some kind, but now we've got to use the computer's own resources to read the keyboard and figure out where we were in the buffer and store what we read in the next byte of the buffer. And so then we need to return to what we were doing when we were so rudely interrupted, but leave the machine in exactly the same condition as we found it. So this is where the stack brilliantly comes in, because remember, it's this beautiful sort of flexible scratch pad, which as long as we pull things back from it in the reverse order we stored them, we get them all back. And what's cool is that the program we interrupt can be using the stack too. We just need to make sure we put everything back the way it was. So our interrupt service routine knows that it's going to use some of the registers in the computer, which were probably in use when this interrupt service routine got invoked. So it pushes the values stored in those registers onto the stack in a certain careful sequence and says, okay, I've saved things. Then it reads the data from the keyboard, figures out where it needs to store it in the buffer, does so, and then it needs to clean up after itself. So what is to say is it needs to restore the state of the machine to exactly what it was when it got interrupted.
Now Jimmy has an interesting question in the chat room.
Uh-huh.
Is this recursive? In other words, what happens when you interrupt an interrupt?
Well, that's a very good point. Now, in this PDP-8 model, there is a problem, which is that when the interrupt occurred, the remember where we were got stored in location 0. So imagine that while we were doing this work in this interrupt service routine, another interrupt were to occur. Well, what would happen is where we were would get stored in location 0, and we'd start executing at location 1, like we said. Well, that's horrifying because we had already stored in location 0 where we were when the first interrupt occurred. Now another one has happened while we were still in our interrupt service routine, which wiped out the record of the first one. Well, naturally, there was a way, there are several mechanisms that come into play here. The first is that the hardware disables interrupts as part of its servicing of the interrupt. So even in the very earliest machine, like the PDP-8, they understood that there was a danger with the architecture that they had. So the act of the computer doing this interruption, storing where it was at location 0, and then executing from location 1, the act of it doing that disables further interrupts. So what that does is it prevents exactly the problem that I just stated of an interrupt occurring while we're still in the process of servicing an existing interrupt. So that prevents there being a problem with recursion. Now, what happened as we moved forward in architectures is things naturally got more complicated. It was recognized, for example, that there were some peripherals that were high speed, like a tape drive or a disk drive, which were generating data or requiring data at a much greater rate than, for example, a teletype or a keyboard. And so the notion of priorities of interrupt priority came into being, where a interrupt would be serviced only if the interrupt, if any interrupt was in the process of being serviced, if the new interrupt coming in was a higher priority than the interrupt that we were in the middle of working on. So that's confusing unless you listen to it a few times. But what that meant was that you could have a low priority interrupt assigned to the keyboard and a higher priority interrupt assigned to the disk drive or the tape. And by agreement of the architecture and the programmers, a higher priority interrupt could interrupt the work being done by a lower priority interrupt. And that required a fancier architecture. For example, rather than having just a single location like location 0, you might have a block of locations, call it 100, 101, 102, 103, 104, 105. That is a location for each priority of interrupt. So that would allow, that meant that different priorities of interrupts stored their interrupted data in different locations to prevent a collision. So again, mechanisms were created that allowed that. But the concept here, the main concept is that we've gone from a system where the starting state determines the entire future of the computer, which would be the case, for example, of us computing pi, where we're just following instructions one after the other ad infinitum, to a very different system where we're now able to respond in essentially in real time to physical events happening in the real world. And thanks to this ability for the flow of our instructions to be interrupted at any time, suddenly other code completely unrelated, perhaps, to what we were doing is being executed. That other code, it promises that when it's done, it will put the machine exactly back to the way it was. Then it returns, because the location where we were has been stored in memory, it treats that like an indirect pointer, remember? So it's not the location, but the contents of the location. So it does, for example, an indirect jump through location 0, where the location that we were executing has been stored, which actually takes us back to where we were. The program that was running has no idea that all just happened. If it were really fancy, it could sense that time had been lost. And in fact, that's the way some of the anti-hacking technology that has existed, like anti-copy protection, or copy defeating, or anti-debugging, because things like debuggers will be breaking the normal flow of execution. Time is lost. And so it's technically possible for that software to sense that, wait a minute, some time has been lost between this instruction and the next one. But in terms of its own sense of the machine and the contents of the registers and what's going on, it would have no knowledge that what had just gone on had happened. It was completely separate from it. It could look around the computer and see evidence of things. For example, it might be keeping an eye on the buffer, which is being filled. The fact that it's being filled is sort of magical to it. It every so often it looks at the input buffer and it sees new characters are appearing, and there's like a buffer pointer that says here's how full the buffer is, and that's changing magically, sort of by itself. It's actually being done by an interrupt service routine reading those characters from the keyboard. But that activity no longer needs to be monitored that closely. The actual main program, just kind of keep an eye on it lazily and decide if there's enough characters yet for it to like get them all at once and go maybe move them somewhere else or do whatever it's doing. So it's an incredibly powerful advance in the technology of the way computers work, which has been responsible for taking us sort of to the next level of allowing computers to interact with us in a very rich way.
It's amazing how this all pieces together.
Yeah, and not that tough.
No, it's not at all.
If our listeners listen carefully, they now understand what hardware interrupts are. Right. And it's sort of like, duh. I mean, that's how they ought to work. And that's how they do. That's all there is to it.
Well, I think the thing I like about this series is that it's almost that it has to be this way. It's like, well, these are the problems you have to solve, and one by one you solve the problems, and it just kind of inevitably almost is this way. I guess there are other ways you could solve it, but this is such an easy, straightforward, logical way to do it. It's like there's a certain inevitability to it, is I guess what I'm saying.
Right,
Yeah.
right. I think it follows logically. One concept follows logically from the next. I mean,
Right.
some of these innovations were brilliant. The notion of a stack, the idea that you could have a stack pointer, where you'd sort of give it a region of memory for it to worry about, and you could just kind of give it things, and then as long as you took them back in the reverse order, it would remove them from the stack in the reverse order that it had pushed them on the stack, creating this incredibly flexible facility for having like temporary storage in the computer. I mean, that was a brilliant addition.
I love the stack. I
Yeah.
just love it.
I did mention that I would talk a little bit about Windows
Yeah.
when we were talking about applications freezing.
Right. The message event or the event key.
Yeah, the message loop, it's called.
Right.
One of the first things a Windows programmer learns, and this may be less true now than it was, things like Visual Basic and some of the more recent languages sort of obscure the reality of what's going on inside of Windows. But the original concept with Windows was that programs that Windows itself, the Windows environment, before it was even an operating system, when it ran on top of DOS, it would hand programs tokens that were called messages. It would hand them messages, which was just a value, a value from 0 to something, which represented an event. And so it was also called the event loop sometimes, or the message, the message loop. And the idea was that the code that the programmer, a Windows programmer, would write would ask Windows for the next event. And in doing so, it was turning control back to Windows. That is, it would say, give me the next event. Well, if there wasn't a next event that affected that window, then the software would just sort of wait. It would wait for another event to occur. And that was how you could have multiple windows on the screen that sort of seemed to all be alive at once, all active at once. That is, you could grab it and move it, or you could type in one. You could do different things. In fact, only one was receiving these Windows events. And so, and as the application processed these events, displaying text or moving the window around or resizing itself, whatever the event told it to do, the window was animated. Well, one of the things that could happen is some applications take time to do something. Maybe they're copying a file to the hard drive, or they're doing some encryption, for example, some serious number crunching that's going to take many seconds. Well, if a Windows programmer didn't really understand the way to program Windows, they might, upon receiving an event saying do the work from a button, because buttons, when you press buttons or you select menu items, those just generate messages. Everything in Windows is a message. So the programmer might just go off and do that work, like start doing some big encryption project. The problem is, while he's doing that, he's no longer asking Windows for any new messages. So when Windows sends a message saying, hey, someone's trying to drag you to a different location, the window, that window won't move. Not because anything's broken, not because anything's hung. It's just that the programmer of that Windows application didn't consider that something else might still be going on while he's busy doing work. It's very much like this polling problem that we just talked about, where if we didn't have interrupt system and the program wasn't going and checking back often enough to see if a new character had been typed, it could miss some. So the proper way to write a Windows application is with something called multiple threads. And in fact, the next topic we're going to cover in 2 weeks after next week's Q&A, I call it the multiverse. Multi-core, multi-processing, multitasking, multi-threading. It's multi-everything. What is all of that multiness at all the various levels that it can occur? We now have enough of an understanding of how computers function to tackle that. But the idea, briefly, of multiple threads, which we're going to cover in detail in 2 weeks, is that it's possible to sort of split off another execution ability from sort of within your program, so that you sort of split it so that you could still be asking Windows for any new messages, while at the same time you are inside the same program. You're able to be doing the math or the long time consuming copy operation or whatever it was you were doing. And if programs are written that way, then they do not freeze when they're just busy doing something. If you don't write your program that way, even though there's nothing wrong with the program, it freezes. And people are so used to programs not freezing, that is, staying responsive to the user interface, that they immediately think something's broken. And in fact, this was such a problem that Microsoft added technology to sense whether a program was not responding to its message loop. And that's where we've seen, I don't know when it popped in, like maybe it was Windows 98, where Windows itself will put up not responding in the message bar. I mean, in the bar at the top of the window, as if we didn't know that it wasn't responding. It's like, yes, we know it's not responding because we're clicking on buttons and nothing's happening. Again, nothing necessarily is broken. It's just that the program wasn't written with enough flexibility in mind.
Very interesting stuff. It's very helpful to understand the underlying principles so that when your programs go south, you know what's going on. It's not a mystery.
Yep. And again, there are reasons for all of this.
Mm-hmm. Steve is the greatest. You can find more of Steve Gibson. In fact, 241 episodes of Security Now at grc.com, including 16 kilobit versions for the bandwidth impaired and full transcripts for those who like to read along as they listen. grc.com. We have the shows also at twit.tv/SN. And then in the next few weeks, probably next week, video of this show will be available on iTunes and on YouTube as well.
Oh, yay. Cool.
Yeah. We're doing about a show a week. We don't want to overload the system. But
you have to have meetings, Leo.
Oh, God. Before the show began, Steve and I was talking, because Steve has always said, he regretted getting his company so big. How many employees did you have?
We had 23.
Oh, man.
And that was about 20 too many.
And that's how many you've got now is 3.
Yep.
You right-sized. I remember one of the pieces of advice you gave me when I was first starting the business is don't get too big and don't have too many meetings.
Yeah, I once discovered years later a Grandview outline. Remember Grandview? That was a really good outliner.
Yeah.
And it was an outline that I had written for a meeting that we had about our meetings. And I thought, my God, even our meetings were having meetings.
That's bad.
So, yeah.
That's bad. Yeah. You have to have meetings as you get employees because the only way you can communicate. You got to do it. But it's a time sink.
Yeah.
And I'd rather be on the air.
We'd rather have you on the air.
Well, it's just like you. You'd rather be programming. Doing what you do best.
I really would.
But it's hard to have. But at the same time, if you want to have control of what you do, you have to have a business. You have to run your own business. It's difficult.
Yep.
I need interrupts in polling instead of meetings. Actually, that's what I get. You watch. As soon as we wrap this show up, I'll be interrupted, and I'll put them on the stack. Steve Gibson is at grc.com. Don't forget, too, that's where the SpinRite program is, everybody's favorite hard drive maintenance and recovery utility. Somebody just asked in the chat room, what happens if the power goes out, as it did for him when SpinRite's running? Is that bad?
SpinRite does everything it can about making sure that it is able to be safe and survive through a power outage. It's been tested for back when SpinRite was being reviewed actively by reviewers. They'd pull the plug out several times and plug it back in. They go, hey, nothing broke. It all works. Like, yep, I spent a lot of time making it be safe.
Yep. So there you go. GRC.com. Also, don't forget, there's that great DNS benchmark. There's Wizmo. There's so many great free programs there too. GRC.com. See, Steve, we will see you next week. We'll have a Q&A episode. If you've got questions you'd like to ask Steve, if this has raised any questions in your mind or any security questions, go to grc.com/feedback. There's a form there for you to ask your question, and maybe we'll use your question next week.
Okay, my friend. I'll talk to you then.
Thank you, Steve.
Bye-bye.
Security Now.
So, the multiverse. This is part of our basics of computing, right?
Yes. We discussed 2 episodes ago the concept of a stack, which is one of the fundamental core principles that underlies all current computing. I mean, there just isn't anything you could replace it with. And visually, just to remind our listeners, you can sort of model it on the stack of dishes in a cafeteria where there's like it's spring loaded. The idea being if you were to place dishes on this stack, they sort of are absorbed by it. That is, they go down into this well, and as you remove them, you naturally get them in the reverse order that you put them on. So the way the computer uses this, say that you had 4 registers and you needed to save them somewhere safe while you were doing something else with them, and then later you wanted to restore them. Well, you could simply say, push register 1 on the contents of register 1 on the stack, push the contents of register 2 on the stack, the contents of register 3 on the stack, the contents of register 4 on the stack. And you don't have to worry about where the contents went. This abstraction, this cool idea of a stack where it's a region of memory with its own pointer, the stack pointer, which automatically advances to always be pointing at the top of the stack. Then you, in our example, you do anything you want to with these 4 registers, not worrying about disturbing their contents because you've saved them on the stack, as the jargon goes. And then when you're done, you would where pushing something is the term for putting it on the stack, popping it is the term for removing it from the stack. So you would pop the stack into the contents of register 4, pop the stack into the contents of register 3, pop the stack into the contents of register 2, pop the stack into the contents of register 1. That is in the reverse order. So just as the plates would go down and come off in the reverse order, so does the contents of the stack. And the point is that this gives sort of a place that as long as you always back out of what you're doing in the reverse sequence that you went in, the stack is your friend. It always provides you what you're expecting. And so that's one fundamental principle. The second we talked about in the last episode, which was hardware interrupts. The idea being that if you wanted to do a couple things at once, if you wanted, for example, if your software program wanted to be printing, well, a printer operates vastly slower than the code running in the computer. And that means the printer can at some level only accept 1 character at a time. Say that it was like an old style teletype where you're going ching, 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 10 characters per second, typing them out on a yellowish kind of roll of paper. You don't want to sit around in your program waiting for the teletype to say, oh, I finally got through printing the A. Now I'm ready for the next character, whatever it is. Because that would require that your program could do nothing else at the same time. It would just have to sit there watching the status of the teletype until it's ready to accept the next character. So this notion of hardware interrupts was generated, where you could have the hardware interrupt your program, which is off doing something else. And that interrupt, what's called an interrupt service routine, which services the hardware interrupt, it would yank control away from your program, just right in between the execution of any two instructions. You would never know when it was going to happen. In fact, that program running in the foreground, it would sort of even be unaware that anything had happened, because in between successive instructions, control would get yanked away from it by the hardware interrupt, which would save the registers, whatever they happen to have in them at the time, which would then free up those registers for its own use to, for example, get the next character in an I/O buffer and hand it to the teletype and start that being printed. Then it would restore the previous interrupted state of the machine and jump right back to the instruction that was about to be executed in the normal main foreground process. So hardware interrupts were the beginning of allowing us to do multiple things at once. Well, the next evolution of that is when we said, wait a minute, we actually do want to do more things with a computer at once, not just printing in the background, but what about time sharing? What about having multiple users who are all able to use the same computer? And of course, time sharing was a big innovation that we saw in the early 70s, because these computers were many tens of thousands of dollars. And it became clear that, well, we've got this hardware which is much faster than a single user. I mean, even someone, Bill Gates, in 1973, at Harvard, using the teletype on one of these early machines, he was typing relatively slowly. And I mean, because you couldn't type fast on those machines. You could only input things at 10 characters per second, no matter how fast a typist you were. And so what they realized was, wait a minute, the computer is sitting around waiting for the next character to be typed in. We could have 10 teletypes connected to this computer, and each user would feel like they had the computer to themselves. The question was, how do you share a machine among multiple users? How do you do time sharing? And what they realized was, we'll have hardware interrupts generated by a timer. And that was it, just that little change. That was a massive innovation, because now what this meant was that part of the hardware, part of the fundamental hardware of the computer would be some piece of hardware, a little timer chip, or a divider, which was dividing down the frequency of the main clock crystal down into something like maybe 100 hertz, or maybe it used the AC line. It actually used the AC current, which is 60 cycles in the US, 50 cycles in Europe. And every time the AC waveform crossed through zero, which would be 120 times a second or 100 times a second, that could generate a hardware interrupt. And the idea was that software, you could essentially have 5 programs, say, all loaded into memory at the same time. And then you'd have a supervisor. And here we begin to get the concept of an operating system. At that point, we'd have a supervisor, which would be supervising the execution of more than one program at once. Well, you needed some way to get control, to sort of yank control back from any one of these programs back to the supervisor. And hardware interrupts was the secret for doing that. So when you started up the computer, you'd have the supervisor, sort of an early form of an operating system, which would initialize the hardware interrupt on the so-called counter timer, or a periodic interrupt, which occurred very often, but not too often. Typically several hundred times a second, something like that. Maybe 1,000 in later faster machines, but initially, you were basically slicing up time based on these interrupts, and every time the timer expired or the AC line crossed through 0 volts, like 100 or 120 times a second, that would generate an interrupt that would give control back to the supervisor. It would look to see how much time had gone by and decide if the same program should keep executing, or maybe if it was time to give somebody else a chance. And so essentially, all of the programs which were running at once, sort of, as we know, computers don't actually run things. Well, actually, they do later on. When you have multi-core, they actually are running more than one thing at once, which we'll get to in a second. But back then, they were time slicing. They were giving, often in a round-robin fashion, that is program 1, then program 2, then program 3, then program 4, then program 5, then back to program 1. This supervisor would get control and then hand control back to the next successive program. Meanwhile, each of those 5 programs had essentially been interrupted. So execution would start on the program, and after this period of time, this clock interrupt would occur, yanking control away from that program, so putting it in sort of an interrupted state, which was fine. It would just sort of patiently sit there until the supervisor decided it was time for it to get another time slice, to get some more slice. And so the supervisor would essentially return from that interrupting event back to the program, having restored the state of the machine the way the program had left it, and then it would continue executing just like nothing had ever happened. So this was sort of the first notion of there being a sort of a nascent operating system, the supervisor, that would start up programs, and the supervisor was able to keep track of the passage of time by these periodic interrupts, which had the power, thanks to the hardware architecture, of yanking control away from anything going on at any time. Now, later on, programmers said, okay, well, I've got a program here, and it's nice to be able to have other programs running at the same time, but I'd like my own one program to be able to do multiple things at once. And what was invented was the notion of a thread. The idea being that a traditional, original, sort of older style program could only be inside of itself, could only be doing one thing at a time. That is, you call it a single-threaded program, which is to just sort of say a non-threaded program. That is, it's only doing one thing at a time. But what we realized was the same abstraction, which allowed us to apparently be running 5 programs at a time, could also give you the ability to apparently be actually in many places of a single program at a time, each one of those places being a thread. And so essentially it's like time sharing, or multitasking, which is, time sharing, but within a single program. Thus, that's called multi-threading. And so what happens is when the program starts, it always starts with just one thread. That is, it starts at the beginning of the program. And so it goes along until it decides that it wants to sort of branch out. It wants to be able to, for example, maybe it wants to be in charge of sending characters out to a device while it's doing something else, much like I was talking about before. And so it's literally able to spawn a thread that is like it's able to within the program, it's able to say, okay, create another thread and start executing it at this location. So because in a traditional single core system, the CPU actually only has a single program counter, which can only be in one location at a time. We know that we're not actually executing multiple threads, or in this case, these two threads at the same time. But once again, we have a timer as part of the hardware, which is able to get control back to the supervisor. And so, whereas before the supervisor was dividing all time up into, for example, 5 main programs, now it's more granular. Now it's dividing time up not only among whatever programs may be running, but within those programs among whatever threads each individual program may have created. So this is a tremendous benefit and a very powerful thing that modern programs are able to do, because it sort of gives the individual programmer within an individual application the ability to set different things running and let them sort of handle themselves. You have to be careful. I mean, and this is where some of the skill of programming comes in, because we're, as we do this, we're escalating complexity, in some cases dramatically. For example, you need to be careful about not having the threads collide with each other, or not having multiple threads trying to do something that conflicts with each other, because essentially the threads don't know. They have no awareness of when they're running and when they're not. Each thread sees itself as if it's running all the time, when in fact it's that time is being chopped up among all the threads in the system. You could have many different threads in different processes, that is to say, different programs, and from sort of a thread-centric view, they just sort of see that they're running along, executing, unaware that chunks of time are missing, during which time other threads in the system have the actual access to the processor, and they're running, moving forward. So Intel at one point said, this is all well and good, but what if we actually supported multiple threads in the hardware? What if instead of this threading being a complete abstraction, what if we actually created hardware that could do sort of more things at once? And so this was before multi-core, but this was what they called hyper-threading. And the idea was that you could have multiple program counters and share a lot of the resources of the processor, but for example, have multiple sets of registers. And the idea would be that so long as the programmers set these things up right, you could actually be doing multiple things at once. That is, the hardware could. And so we went for a couple years like that. And then, of course, Intel went to the next stage and gave us multiple cores, where now you actually had full processors, which again had their own program counters, they had their own registers, they had all their own resources. They shared memory. So that was the common thing that they shared, as well as the hardware, like the display and so forth. That is, that they had common access to the system's I/O and also to its memory resources, but otherwise they were independent. Well, by the time that this happened, operating system technology had evolved substantially. I mean, we already had Windows and multiple tasking and multiple threads. And what was so cool about this notion, first of hyper-threading and then of this multiple core, was that you'll notice that our operating system software and the applications we were running, nothing changed. That is, we didn't have to have different applications. We didn't have to have a dramatically different operating system. That is, there was this notion of multi-core support, but from the user standpoint, our systems just got faster. Things worked better. Well, and the reason that happened was that we had already, before that time, there was this mature concept of multiple processes and multiple threads. And the operating system was given the task of deciding what the computer was actually doing at any one instant. And the operating system was jumping the program counter all over the place, giving all these different threads a chance to run until the next hardware interrupt yanked control back to the operating system, where it would decide what to do. And it was the so-called scheduler. The operating system scheduler is, it alone, the optimal strategy for that is the subject of, doctoral theses and whole books on computer science, how to maximally schedule all of these things that are going on simultaneously in the computer. Do you want to allow some things to run with high priority? Do you want some things to run in the background? How do you manage the simultaneous demand across all of this? But what was so interesting was that the abstraction of all these threads essentially running at the same time. That is, in a given program, the threads were set up so they thought they were all going at once. And individual programs in the operating system thought they were all going at once. So when we added multiple cores, they actually could be going at once. And the way we got away with this was there was already the discipline in place about not having them conflict with each other. That is, there was already some inter-process containment so that processes couldn't stomp on each other's memory. And within a process, there was already inter-thread discipline to make sure that these threads that conceptually were all running at the same time behaved themselves and didn't mess with each other's business, essentially. So when we added hardware that actually was able to run multiple things at once, first through this hyper-threading that was sort of poor man's multi-core, and then real multiple core, well, everything just got faster. It scaled beautifully because everything we already had, the whole structure was oriented toward this simultaneity, which initially we were faking out, but later we were actually able to do it. So that's basically the multiverse of contemporary computers. And what we're all sitting in front of right now is all of that going on at once, all behaving itself for the most part. When it doesn't, things definitely go sideways. But when everybody plays their part and behaves themselves, we end up with just an incredibly powerful facility for computing.
It's been fun watching Intel slowly add these capabilities, as you say, with hyper-threading and multi-cores. And they also use something called QPI, inter-process communications, now in the new i3, 5, and 7 chips. They've really gotten very sophisticated about how to do this. It's no longer just time slicing. They're really getting sharp about it. And it does make a difference. And I think the reason that they put so much effort into it is they realized that they couldn't put more megahertz out, that they were getting all sorts of problems past 3 gigahertz. And so they backed off and they said, well, we're not going to have a 6 gigahertz processor. How else can we improve speed? Multiple processors.
Well, and Leo, 3 gigahertz,
That's a lot.
billion,
Yeah.
3 billion cycles per second. Yeah. It's nuts. The first IBM PC was 4.77 megahertz. Right. And we were all thinking, whoa, this puppy it cooks.
I remember very well when we first started doing TV for Ziff Davis in the early, I guess it was 92, 93, 94. And Bill McCrone came in. He brought in the new Pentium, and it was 90 megahertz. And we were all saying, oh, it's so fast. And I remember using it saying, wow, it feels slippery. It's so fast. It's moving around. And that was 90 megahertz.
Yeah.
We are now, more than 30 times faster. In just clock cycles, and then you double the core or quadruple the core. Intel's got 6 core processors coming out. Each is hyper-threaded. That's 12 processes, 12 threads at a time.
Well, and what's really interesting, too, is that while the processor performance has been able to scale generation after generation after generation, main memory stalled, essentially.
Right.
The so-called DRAM, dynamic random access memory, its technology turned out to be stubbornly non-scalable. So, and it's just due to the nature of the way DRAM operates. There are, we hit essentially the physical fundamental limits of its speed much sooner than we did processors. And so what's been done is we've made it wider, that is, so that one memory access is fetching many more bits sort of in width at a time. And then we've gotten very sophisticated with caching, because one of the things that the early researchers noticed was that computers would sort of go over here in memory for a while and work in some loops and do some work in a certain region, and then they'd go over somewhere else for a while and do some work in a different region. It wasn't like they were like the actual execution was randomly occurring throughout all of memory. There was a there was a regionality to it. And so what they realized was that if you had a much smaller but much faster memory, a so-called cache, a static memory that was able to be made to be kept at the same speed as like the registers of the computer, where they could run in a single cycle. What they realized was, well, you might have to wait essentially to read what's in main memory into the cache to get it into the cache, and that would take a while. The processor would essentially, it might be stalled while you were painfully slowly pulling main memory into the cache. But once you got the cache loaded, then the processor could run again at full speed, full sort of local speed, as long as there were, as the term is, a high percentage of cache hits as opposed to misses, so that while the processor was doing things locally, staying there, it was able to execute again at full speed. And so they extended this notion not to just a single level of cache, but to then 2 levels of cache, having a very high speed but smaller and then a semi-high speed but larger, and then like finally main memory, where we just can't make it any faster, unfortunately.
Yeah, in fact, we know L2 cache, that level 2 cache, the amount of that makes a huge difference in overall processor speed.
Yes, and when people are selecting processors, it's also expensive because it takes up chip real estate and it takes up power. And so one of the things that purchasers do is they decide, how much speed do I really want? Because the chips with a larger level 2 cache, the L2 cache, they're going to be more pricey.
Right. It's a great subject. At some point, maybe, I don't know if there's enough for a whole show, but I'd love to talk or hear you talk about cache, the concepts behind caching. Because we see cache all over computing. We used to see hard drive caches. There's browser caches. And, of course, there are these processor level caches. And it's all the same idea, I would guess.
It's absolutely. It's very similar.
And there's a lot of computer science into how you do this, right?
Oh, well, yes, and there's also write back versus write through.
Right.
Do you? And there's this notion of the cache being dirty. That is, the processor also wants to be able to write into the cache. Not only just it's not only that data from main memory is pulled into the cache, but the processor may be modifying the cache.
Right.
So the question is, do you start writing back to main memory when the cache is changed, or do you wait until you have like a different flush event? That is, for example, the cache may be changed a whole bunch of times, in which case you wouldn't want to be writing it back all the time. But then you've got a problem, for example, with multiple cores, multiple processors, because they need to have a coherent view of what's in memory. And if one processor's got modified memory in its local cache on its chip, then the other processor can't see into that. It's seeing main memory. And so it gets very tricky.
Love to hear more about that someday. Very tricksy. By the way, Steve, you've crossed the 1,000 follower count on both Gibson Research and Agile Synapse on Twitter. So 1,000 people now are waiting for your first tweet on Agile Synapse.
I will try not to disappoint anyone.
And I'm sure, but next when we come back, after this podcast comes out, there'll be several thousand more.
Cool.
Who knows? Cool. Let's see how high we can get it.
I will use the Gibson Research Twitter account to let people know what's going on with Gibson Research, and Agile Synapse to let people know what's going on with me. I don't know why anyone cares, but
we do.
We'll see how that goes.
We care, Steve. We really do. Steve Gibson is the man in charge at grc.com, the Gibson Research Corporation. Go there for, of course, this show, both 64 and 16 kilobit versions for people with low bandwidth. There's also transcripts there, show notes, and more. And grc.com is the home of Shields Up, Shoot the Messenger, Decombobulator, Wizmo, all those free things Steve does, perfect paper passwords, and that one thing that he charges you for, SpinRite, the world's best hard drive maintenance and recovery utility. If you don't have it yet and you have hard drives, you need it. SpinRite from grc.com. Steve, we'll see you next week.
We'll do a Q&A
and
answer any questions. So do have our listeners, grc.com/feedback. We'll take you to a web form where you can tell me what's on your mind. I will read them, and we'll choose a bunch of good ones and talk about them next week.
And they're reminding me in the chat room that you might want to turn off email notifications of new followers on Twitter because you just got 2,000 emails. Congratulations.
The good news is I did understand that much, at least.
Steve's no fool.
I had that turned off before I breathed word of it to Leo.
You know who we really hurt with that was the wonderful woman in Auckland, New Zealand, Lisa Tickled Pink, who we just randomly chose on Twit as somebody that everybody should follow, and she got something like 50,000, I don't know, some huge number of emails almost instantly, and I felt bad. She thought she broke the internet. She thought she did something wrong. I feel terrible. Thanks, Steve. We'll see you next week.
Thanks, Leo.
Security Now.
Security Now.
Well, I'm ready if you are. We're going to get to our Fundamentals of Computing series. Kind of the final, although I think networking really counts as still part of it. But the operating system is about as high a level as you can get in the PC.
Right.
So let's hear how operating systems work.
Okay. We began back in the 50s. So operating systems are, today, here we are in 2010 recording this, as of this day, or date, or year rather, not specifically, this particular day, they're 60 years old. Originally, computers back at the beginning had no notion of an operating system. They were just these very expensive, rather limited machines. Typically, they had like word sizes of 32K. Sometimes big ones were 64K. But I mean, that's as big as they got back then. That wasn't a small machine. That was, a big multi-$100,000 installation in a university would have 32K. And so the problem was, how do you make use of this machine? And in fact, over time, as machines grew larger and also a lot more expensive, keeping them busy was the biggest problem, because it would take time to load a program into the operating system. Then the OS would spend some time running, and of course, you've got the debugging of the program to deal with too. I mean, the thing to remember is that computers at this time were rarefied. This was the men in the white smocks on elevated floors with air conditioning, and you had one machine that was basically held hundreds of people in thrall, because their jobs were about keeping this very, very expensive, $500,000 piece of equipment busy. So the original model was what was called an open shop, where the people who had a job to run on this machine would sit down and load their code, load their program into the machine over some length of time, and then work with it for however long it took. Meanwhile, everyone else was standing around tapping their feet, wondering when they were going to be through, because it was their turn to the goal was to keep this thing that was so expensive somehow busy all the time. So this open shop model switched to a so-called closed shop, where you instead of the actual people who wanted the work done doing it themselves on the machine, you created sort of a layer of separation. Now, instead, people submitted their jobs to the staff who were more adept and more expert at using the machine more quickly. So we got a level of efficiency that way. And also, there would be a queue of jobs to be run that had been submitted, so there was a backlog. Well, of course, this meant that people often had to wait longer to get their results, but in general, the goal of keeping this machine busy, being better at keeping it busy, was achieved that way. And so that sort of introduced this notion of batch processing, where there would be a queue of things to do, and people would submit their work into the beginning of the queue, and then experts who were better at processing the data or these jobs in the queue would then do the work. Well, the problem still was that there was a large setup time in between these jobs. So, for example, programs might take, a few minutes to run, but would take half an hour to get themselves set up and going. So people looked at these systems and saw that they were still being very inefficiently used. And the problem was the I/O, that is, typing up punch cards and then having a stack of cards would take a long time to read a deck of cards into the machine because the machine was much faster than the card reader. And similarly, on the back side, ultimately you were trying to print out reports of some sort, and the printer was much slower than the computer. So, and we've talked about this when we were talking about interrupts and I/O, the I/O systems. The idea that the computer could be busy doing other things, and every so often send a character to the printer being so much slower. But here, in a system there was no concept yet of time sharing, of multiprocessing, of doing more than one thing at once. That just hadn't occurred to anyone. Well, and frankly, the systems at the time, they weren't capable architecturally of doing that. There wasn't they didn't have stacks. That didn't come along until later with Burroughs, the early Burroughs machines, the 5000 series machines, first introduced a stack architecture. So here we've got this machine that is 100% I/O bound. It's sitting around waiting for cards to get read. When the program is finally loaded in, then it takes a short time to run it compared to the time it took just to read it in. And then on the back side, once it's done, now the computer sits around waiting for the printer. So again, looking at this, it's like, okay, how do we solve this problem? Well, what they used magnetic tape in order to decouple the slow speed of the physical I/O devices from the much faster speed of the computer. So now what happened was people would punch their cards as sort of like the slowest step of the process. So now you'd have card decks. Then there would be a number of machines which read cards and wrote them to mag tape, because mag tape was much faster than cards. So jobs would get punched on cards, then and that would happen, by some key punch operator that was skilled at running key punch. Then those would get written to mag tape, and as many jobs as possible would be put on the tape. So the tape would be filled up with jobs to do until it was full. Then that would be mounted on taken from this machine that its sole purpose was just to read cards onto tape. Then the tape would be stuck on a large mag tape drive connected to the computer, and it had several mag tape drives that were being used in round robin fashion for input, and another set used in round robin fashion for output. So this mag tape would get loaded, and as soon as the computer was done with the previous mag tape on a different drive, it would start reading in jobs from mag tape drive number 2. Meanwhile, the first one would be rewinding. It would get pulled off and stuck back on the card reading machine. And so you could see, it's like the people were running around spending all their time trying to keep this machine busy. And you can sort of think of it as a hierarchical funnel where slow processes fed into a faster process that then fed into a finally very fast process. The upshot of this was that you finally had this very expensive machine. Thanks to having funneled all the I/O into it, you'd solved that speed problem. You were still running everything one at a time. That is, again, still no notion of the machine doing more than one thing at a time, but at least now you had you'd solved the input problem so that this thing was, the machine itself was now very quickly loading programs off mag tape, running the programs, and then dumping the output back onto one of a number of output mag tapes. The printers weren't capable of keeping up with that. And so you had sort of the same sort of, in the way that you have a funnel on the input, you had an expansion on the output. The computer would fill up a mag tape with output and then switch to the next mag tape that was waiting. The operators would pull that full mag tape off, now take it to offline printing, where that mag tape would then be servicing a number of printers that would print the results out. And so, that was sort of like the next level of how to keep this extremely expensive machine busy. So that notion, that this whole thing was called spooling. And it's funny, I didn't realize until recently, when I was doing some buffing up on the history, that spooling was actually an acronym. It just seemed to me, I mean, I've and I'm sure you, Leo, have heard of, like, spooling this off to tape, spooling it off to the printer. Spooling seemed like, like a spool on or thread on a spool, where you were just storing it somewhere. Turns out that it's an acronym. SPOOL stands for Simultaneous Peripheral Operation Online.
Oh, you're kidding. Spool is an acronym?
Yeah.
I never knew that.
I know. I didn't either.
It makes sense because it's spooling something out like it's a thread. So I thought that's what it was doing.
I always just assumed it was a verb, but it's an acronym.
Holy cow.
Simultaneous Peripheral Operation Online. That's where the word came from.
How funny.
So it was in 1959 that essentially after 10 years of this, fire drill of trying to keep a very expensive single machine busy, that John McCarthy at MIT, who of course famously gave us the Lisp programming language and lots of other computer science in between, he wrote a memo first suggesting the notion of time sharing. The idea being that, and which was radical at the time, the idea being that rather than the entire machine being committed to a job, to a single thing, we would slice up time and handle it in a round robin fashion or in some sort of a priority fashion. But the idea being have many different jobs operating in the machine at the same time. And in fact, McCarthy proposed the notion of terminals being connected to the machine in such a way that the individual users all thought they had exclusive use of the machine. He recognized that the duty cycle between, of someone typing characters and how rarefied character typing is would allow essentially the same kind of funneling as was being done with key punch operators concentrating onto cards, concentrating onto tape, concentrating onto the machine. He said, hey, you could achieve the same thing if you had real-time connection among many different consoles, all feeding into a machine which was able to look at them all at the same time. And so, which was at the time, a huge change, conceptually a big leap in the way systems operated. So we talked last time when we talked about the episode called The Multiverse. I guess that was actually 3 weeks ago, because we had a Q&A and then we had the Portable Dog Killer episode. Oh, and a Q&A before that. So I guess 4 weeks ago. Anyway, we talked about in the multiverse this notion of we've looked at this concept of the stack, which is able to store the state of the machine, and that hardware interrupts that were caused by people pressing keys or a printer saying, I'm ready for another character, they could steal tiny bits of time just to fill an input buffer or to empty an output buffer, and then switch right back to what was being done before. And so this notion of interrupting the flow of instructions and saving the state of the machine so that you can restore it when you come back, and jumping somewhere else and doing something, it's the growth of that created what we now have with the current operating systems. So operating systems over time have had various structures. Before there was a theory sort of operating systems, before we had enough experience, they were just sort of big monolithic things. The idea was that programs would be clients of the operating system. There would be sort of this code in the machine which is always there. That's the part that's not changing. Programs would be transient. They would come and go and run for, say, some length of time while their user was running them, and then they would be terminated, releasing their resources. And one of the things that quickly happened with this notion of time sharing was that the designers, the people wanting to use these resources, were a little bit aggressive, because notice that one thing happens when we chop time up, which is different from when we process jobs sequentially. If we process jobs sequentially, each job has the entire machine to itself while it's running. That is, however much RAM, for example, the machine has, the job can fill all of that RAM. But with McCarthy's notion of time sharing, things get a little complicated, because if you're going to have many programs running at once, then they've all got to be in RAM. That is, now, and I'm saying RAM because I'm used to today, but that was core. Yeah, and 64K, remember, was the kind of size of core these machines had. So one of the notions that was created was this notion of swapping. And swapping was a sort of an early form of what we now call virtual memory. We'll talk about virtual memory and how that works a little bit later in this episode. But with swapping, the idea was that you would have fixed size partitions in core. And you might have, say, 16 users using the machine at once at terminals, and the single computer that was being shared might have an operating system that used some piece of core. And again, back then, the operating systems were all written by hand in assembly language, which is sort of just an ASCIIized version of machine language. So a one-to-one correspondence between instructions that had been manually written by the operating system creators and the code that's being executed. And then whatever memory was left over might be, for example, divided into 4 partitions. So you might have, say, in a 64K machine, you might have, normally these operating systems were relatively small because they weren't doing that much. You might have 8K taken up by the operating system, and then the balance of that memory, like 60 or like 56K, would be divided into 4 equal size pieces. Those would be partitions, and you'd have, however, 4 partitions and 16 people. So obviously we've got a problem, because what these 4 partitions mean is that the system can only actually be running, can be quickly jumping between 4 programs at once. So swapping was the solution they came up with. They said, okay, we'll have a drum, and drum memory was without, this predates disk memory, and we'll have partitions on the drum to essentially hold all 16 of these partitions, and we'll swap them one by one, or actually 4 at a time, essentially, into the machine's memory. So 4 programs can be running, and after a program had run its allotment of time, it would be sort of frozen and swapped out onto the drum, and another waiting program would be swapped in to one of these partitions. And then it would be, being now in core memory, it had the opportunity of running. So that was the way back then, they solved the problem of needing to have essentially more resources, because now they were trying to do this time sharing. They needed to have more resources than the machine could technically support, because oftentimes you couldn't just add memory even if you had the budget. Remember that the instructions were so short that the instructions themselves couldn't address more than 64K words of memory at the time. So originally, there was no sort of theory of operating system design, because no one had ever designed one before or written one before. So operating systems started as sort of big monolithic systems, and they sort of grew awkwardly and not very elegantly. And back at this time, a lot of this research was being done, if not all of it, primarily in universities. So the university sort of model is one to say, okay, wait a minute, time to reset. This operating system has gotten unwieldy. No one really, the people who wrote it graduated got their PhDs and left a couple of years ago. So we've got these huge chunks of code that no one here knows about anymore. We need to just start over. One of the approaches that was taken was what was called a layered approach. As people began to apply real sort of academic discipline and thinking to the design of an operating system, they said, okay, wait, let's try and do this in like a layered fashion. The bottom layer will be just the processor's own usage and allocation and the division of time. Then on top of that layer, we'll write the sort of the management of memory and the drum swapping code. And then on top of that, we need to have some operator interface that is able to control starting and stopping these jobs running. And then on top of that, we need to have input output so that the operator's console can receive input and then display the output. And then on top of that is user programs that are running. So there was this attention. They began to get the concept of some sort of structure, a hierarchy, a layering of the way things were being built on the OS. The next problem they ran into as systems became larger was again one of complexity. The problem was that they recognized quickly that mistakes that were made in the operating system brought the whole system down. And the operating systems were continuing to sort of grow without end. So at one point, this notion of a microkernel was proposed. The idea being to recognize that the kernel is this privileged resource where it's sort of the supervisor, the monitor of all the programs that are running on it. And it provides services, which we'll be talking about in a second, to the programs that are running on the operating system. The problem with it getting big is that there's a given number of mistakes that are going to be made per 1,000 lines of code, and that just sort of seems to be an immutable fact of the way software is being written. So if that's the case, and if mistakes are bad, and they're especially bad in the kernel, because a mistake in the kernel brings the whole system down, as opposed to just a user program being aborted, but everybody else gets to keep running, a mistake in the kernel, and it's game over. So the logic was, make it as small as possible. If it's as small as possible, it'll have as few lines of code as possible, and based on the average number of mistakes per line of code, there'll be fewer mistakes. So the microkernel approach was specifically designed in order to minimize the number of bugs that could bring the system down. on top of that then was created this notion of a client-server model. And that's what we now see in modern day, for example, Unix systems and in Windows, where you have a relatively small kernel which provides the fundamental services to both user programs and services which are running on the system. So the idea is that the kernel is very small, and then but also not very capable. It does the fundamental sort of lowest common denominator things like handling processes, dealing with threads, slicing up time, managing memory, managing file systems, the sort of the core services that the operating system, that everything uses in the operating system. And then you've got two classes of programs essentially running on top of that is using those services. You've got service programs which provide additional features, much richer features. And then you've also got the actual client programs that are clients of those services. And that's sort of the model of operating systems that has evolved. We've sort of been talking, we were talking originally about mainframe operating systems and evolved into this notion of personal computer operating systems, but it's worth noting that there are operating systems of some sort in a microwave oven. As we were talking about complex systems running in cars, there's operating systems in cars. I mean, there's operating systems literally in anything today that is complex enough to have a computer in it. There will be some sort of operating system. So there's also a hierarchy sort of in OS scale. Mainframe operating systems still exist today, running big, Cray hardware. Huge, large insurance companies will have huge mainframes still with I don't know if the guys run around in white coats anymore, but, large scale systems that are still doing oftentimes batch processing, that are producing reams of reports and data, and also lots of communications. They tend to be very I/O heavy. Coming down smaller, we've got server operating systems, which are still large, capable hardware that are then servicing the needs of many people at once. Then we come a notch down to the personal operating system running on our computers. We're having typically many things going on at once, but generally serving one person at a time. And then handheld operating systems that are running, smartphones and PDAs still have a computer. There's still a core set of services that those are offering to programs that run on them. And then the notch down are embedded operating systems, and that's the class of OS where you don't think in terms of there being an operating system. There's no file system. There's no sort of generic user interface. This is an embedded OS is, for example, what's probably in our cars and microwave ovens, consumer appliances, DVD players and things. We see a very purpose-specific user interface where there's a display of remote control, buttons that you can push. But back there, in there, is an OS. There are a number of companies that license these for the common chips, and they're embedded and also sometimes real time. An RTOS, an RTOS, a real time operating system, is typically a small system that prioritizes time over features. That is, it guarantees that code that's running on it will be responsive and that nothing else going on in the OS will tie up the computer's resources more than a certain amount of time. So there's a guaranteed latency in the operating system's ability to respond to the tasks that are running on top of it. So what do all these operating systems do? What features do they offer? Well, one way or another, the mainframe operating systems, server operating systems, personal operating systems, even handheld operating systems, that is everything above sort of the embedded operating system, they provide a means for loading a program from mass storage into memory. We know now that processes, are typically composed of, well, at least one, but in many times, many more than one threads, where threads are sort of an abstraction of a series of instructions that are being executed. A program could very well just be single-threaded, as is the terminology, where it starts and the program executes only conceptually one thread of execution at a time. So there's only, for example, one program counter associated with that process because there's only one thread that is at a specific location at any point in time. And as we explained in the multiverse, you can have multiple threads because a thread is able to spawn or fork another, essentially another conceptually asynchronous stream of execution, so that it's able to go, this forked or spawned thread is able to go off on its own and do something else. For example, it may be responsible for reading the keyboard or updating the display or doing some other things that are sort of asynchronous to the main work that the primary thread of the process is doing. So the operating system is the thing that oversees all that. It has some hardware, a timer, which is generating interrupts at a given frequency. That interrupt is what's responsible for yanking control away from individual threads running in individual processes and getting control back to the operating system. When that happens, the operating system takes a look at what's going on and decides if the thread should continue running, if it's time to give it to a different thread in the same process, or if that process has used up its allotment of time to bring back to life a thread in a different process that was previously suspended, in which case it restores the state of a given thread as if that thread had never been stalled, and just continues executing where that thread let off. So that's the job of scheduling, which is the subject all by itself of books on operating system theory. Scheduling is amazingly complex, and it's easy to sort of stand back from a distance and say, okay, well, this just has to divide time up among all these threads. But it turns out that when you start actually doing it, there's all kinds of complexity with deadlocks and stalls and competing priorities. And if something has a low priority and the things with higher priority never take a breath, then the things with low priority never get a chance to run. So that's not good. So it's like an amazing mess of special cases. And again, has been the topic of many doctoral theses over the years. One of the other things that operating systems do is allow inter-process communication. That is, they support a means for allowing processes to communicate with each other, which is often something that co-working processes want to be able to do. You want to be able to have some sort of communications between them, even though the operating system is all about inter-process isolation. In some cases, you do need to facilitate communication. The operating system provides that mechanism because there is otherwise no direct means for example, for one program to mess with another program's memory. You want to manage that carefully to prevent mistakes from happening, and also, of course, to prevent deliberate abuse from being possible. One of the other things that all of this relies on is memory management, which we've talked a little bit about, but never really directly. The idea is that that in every case, all these operating systems basically produce an abstraction of the machine's underlying resources and of time. Time is and the passage of time is an abstraction as well, because from a thread-centric standpoint, a thread just thinks it's executing all the time. The thread has no awareness that time isn't all its own, that it isn't running all the time, because control is yanked away from it and its state is saved. Then the state is restored and it picks up exactly where it left off. So from its standpoint, it's just running all the time. In fact, we know that's not the case. There's thousands of threads in a typical system that all believe they're running all the time, when in fact, on a single core system, only one is actually running at any time. In a multi-core system, you can have as many actual threads running as you have cores. So the operating system is essentially creating an abstraction of the underlying resources. One of the resources is memory. Processes can, much as was the case back in the days of early time sharing, where it was possible for a process to be sharing memory with other processes. Back then, you could only have as many partitions of a certain size as there was room left over after the operating system had been accounted for. In this day and age, we've got this notion of virtual memory and the ever-present. For example, Windows users are familiar with the paging file, or the sometimes still called the swap file. The idea being that processes believe they have a much larger amount of memory than they actually do, and this is hidden from them. This reality of how much memory they have is hidden by the operating system. If the process attempts to execute or read or write memory outside of what's currently loaded in the system, the operating system, using this virtual memory technology, will get control literally at the instant of a program's attempt to read or write memory that is not physically loaded at this time. The operating system, that creates what's called a page fault. The operating system gets control at that instant, sees what's going on, and says, the program is trying to access memory, which we've had to swap out to the hard drive because of limited resources. Other programs needed to use physical memory. So what happened was that memory was paged out, as is the term, onto the hard drive, while another program that was running was actually using the underlying physical memory. So when a program attempts to use memory which doesn't physically exist, it's been paged out, the operating system gets control, sees what's going on, decides, okay, do we page this in? Do we suspend the process? There's a whole bunch of decisions to be made. As I said, scheduling is itself a huge issue for operating systems. Typically what happens is, because physical I/O is necessary and always takes time, the act of the process touching memory that isn't physically located, or that isn't physically present in the system, suspends it. It's the memory is queued up to be written or to be read from the system, except that there's no doubt some other process using the physical memory that's in use right now. So that needs to be written out to the swap area so that the memory which had been swapped out can be brought back in. Like I said, this gets really complicated very quickly. But the bottom line is, what ultimately happens is the so-called swap file or paging file or virtual memory file, it's a oftentimes very large extension of the physical memory in the system. And we talked last week, or last time we were talking about this, about the notion of caching, where the processor had very fast access to its own registers. And then it would also have a cache of maybe 8, 16, 32K in the old days, megs now, maybe several megabytes. And that would be a copy of what was in physical memory that would be maybe hundreds of megabytes or a gigabyte. Well, if you can see that forms a hierarchy from the register in the chip to the cache, and oftentimes there's a level 1 cache and a level 2 cache, level 1 being smaller and instantly fast, level 2 being larger, not quite so fast, and then you have physical memory. Well, virtual memory is the last largest layer of this hierarchy, where it represents sort of this super physical memory that is really slow in as much as it's written out on mass storage, which is typically a rotating medium in this day and age. And so it's very slow to read and write, but it's very large. And so that's sort of the virtual memory forms the final layer of this multi-layered memory hierarchy, where we get smaller and faster all the way up to the individual register of the machine. And the operating system manages all of that. One of the other things the OSs do is support a file system, so that the programs running on the operating system are able to, again, see an abstraction known as files, which exist only because the operating system creates that abstraction for the programs that are running on the OS. It knows about the physical organization of the media, the mass storage on the system, but hides all of those details from the programs that are running under it.
Steve is taking a small drink at this point. For those of you listening at home.
My throat was getting scratchy, believe it or not.
Well, you said it wasn't a lecture, but this is a lecture, but a great lecture. I'm really enjoying it. It's fascinating.
So one of the things that happens is that notice that we've got floppy disks, which are small, 1.44 meg, for example, in the famous instance of the IBM PC, and have a physical organization with some small number of sectors around some small number of cylinders on two sides. But we might have a multi-platter hard disk that's got thousands of sectors arranged around millions of cylinders and multiple platters. Well, the operating system's drivers understand these specifics of the hardware that they're driving. All of that is hidden from the programs that run under the OS. The program sees this abstraction of named files, and so it's able to say to the operating system, hi, open for me this file of this name and let me read it. And the one of the main innovations that operating systems had was that this concept of, I don't care where it is, I don't care what media it's on, And in fact, even as far back as remember Unix and CP/M, there was this notion of this could be paper tape or this could be a hard drive. There was this disconnection with the I/O system and the physical devices that were running underneath the operating system. So this abstraction is provided by the operating system, and then there's also an abstraction provided by I/O drivers, where the operating system would have a defined mechanism for interfacing to, for example, file system devices. And different drivers would be used to interface the operating system to very different storage mechanisms. So you have a floppy driver which is able to answer specific uniform requests from the operating system, translating them into the instructions needed to work with a physical floppy drive hardware. And you'd have a mass storage driver, for a given hard drive, which is able to take the same operating system requests as the floppy driver, but in this case, translate them into very different specific functions for its hard drive. So again, we create these boundaries of abstraction where the entities on each side of the boundary have agreed upon a protocol that is uniform, typically documented, and not changing. So drives can get bigger. The drivers may need to change over time, but that agreed upon protocol at the boundary of the driver and the operating system, or even the operating system and the application program, that doesn't change. And so that allows things on either side to evolve over time, which was another major innovation in operating system design. And then finally, the last thing that's come along in recent operating system architecture on top of file systems and I/O is security, where there's an increased notion of both wanting to prevent mistakes from compromising the system and wanting to prevent deliberate malicious intent from compromising the system. So there's this notion which is layered on top of everything of privilege. The idea that certain files can be privileged, certain memory regions can be privileged. Essentially, there's this notion of ownership and rights which are applied to all of the objects within the operating system, right down to and including the individual thread of execution. Threads can own objects, can have rights, and everything scaled all the way up from threads and all the other abstractions that the operating system creates can have rights. And so in addition to everything else the operating system is already doing, it also has to check the security. It has to make sure at the level of the individual action, it has to make sure that action is permitted, that the thing asking for something to be done has rights to do that to whatever it is asking for it to be done to. So OSs have gone from starting off being basically a loader of code for a system which was struggling to be used enough to what we have today. We're all sitting right now. You're hearing this through probably a device with an embedded operating system in it.
Almost guaranteed.
Yes.
I don't think you could play it back any other way.
No, there's no other way to play it back.
Yeah.
Leo and I are sitting in front of computers that are right now, as we sit here, have thousands of threads all running, all competing for resources, using the hardware, somehow staying out of trouble. And to me, it's amazing.
Absolutely. Absolutely. It's truly a miracle that these things even work. It's amazing. Are you done?
I think that's it.
Wow.
That's operating system.
I tell you, you got to put these all together on a DVD or something, and we'd have the complete set of building a computer from scratch. What fun. Now, next week, it's a Q&A, so if you've got questions for Steve, if there's anything you heard today that you have a question about or anything in the security world, you can get a hold of him by going to grc.com/feedback. That's his feedback form. Easiest way to do that. GRC is Steve's site, of course, now blog-enabled.
Yes, and I would encourage our listeners to go to blog.grc.com and subscribe so that they'll get a short note from WordPress whenever I have some information. I'm sure I'll be talking about important things here on the podcast as well. And of course, I've got my personal blog, steve.grc.com, if you want curious about the sort of things more in a column format.
And follow Steve on Twitter. He's SGGRC on Twitter, SGGRC. And that way, that's his early warning system. I presume that anything big would come across there first.
Yeah, and, navel lint.
And navel lint about vitamin D and the Ford Pinto. It is GRC is the place to go, though, for Steve's great programs. Not just SpinRite, which is absolutely the world's best hard drive maintenance utility. You got to have it if you've got a hard drive. But also all the free stuff he gives away, like Shields Up and Wizmo and all sorts of stuff. GRC.com. You'll find 16 kilobit versions of the show there, as well as the 64 kilobit versions in high fidelity. The transcripts, the show notes, it's all there. grc.com. You can watch video of this show. Steve doesn't post that, but we do at twit.tv/SN. You can even subscribe to that if you want to put it on your iPad, pod, phone, whatever it is you've got. You'll need Threads to view it, I'm afraid. grc.com. Steve, we'll see you next week. Next week, Q&A time.
Yep. Thanks, Leo.
Security Now.
All right, Steve, I'm ready. I've got my my thinking cap on. Some may call this a dunce cap, but it's a thinking cap, and I'm prepared to think. Tell me, sir. Where do we go now that we've been building a computer?
We've established a beautiful foundation over the series that we've covered so far. The idea being, of course, to demystify what a computer is, how it works, what it does. We know that there's a main memory and there's a program counter that points to a current address of a word in memory, and that word is composed of a bunch of bits, and that those bits are broken into fields, the most important field being the so-called opcode, the operation code. The pattern of bits in there describes to the computer or specifies what the computer should do with that instruction, each one of these being an instruction. And the rest of the bits in this word provide the parameters for the instruction. For example, it might be clear the accumulator, or it might be load from a location in memory into a register, or store the contents of a register into a location in memory. So when we've looked at what the stack does, the notion of the convenience of being able to have sort of a scratch pad where we can push things on and we can pop them off in the reverse order, so that as long as we kind of keep track of our own housekeeping, we don't have to preset aside areas to read and write into. Everybody's able to share this as long as they do so carefully. And so we've talked about subroutines. We talked about hardware interrupts and how interrupts from physical I/O devices, which are much slower than the computer is running very fast, are able to be used to yank control away, yank the program counter to somewhere else, allowing the computer to service this interruption, send characters out to a slow printer, for example, and then return to the code that was running as if nothing had happened. So we've got this architecture, and that's where everything began. What I want to do today is describe the evolution from there to now. That is, what happened after this, and what were the pressures that were on the industry and on the engineers and on the companies that evolved this from that very clear and sort of basic beginning to present day machines. So one of the things that happened as hardware became less expensive and programmers were complaining to the engineering team that, like, hey, it'd be nice to have some more registers here. We've got the accumulator, but we're having to use it sort of as a scratch pad for main memory. We can't really hold much of what's going on in the accumulator. So they said we need more registers, more accumulators. And so the engineers said, okay, well, that means we're going to have to make the word longer because we're going to need some more bits in the instruction to specify which register you want to load and store and add and so forth. And so the engineers said, yeah, okay, fine. Do whatever you, or the programmer said, that'll be fine. So words got longer. And then some of the engineering guys said, well, a simple instruction like clear a register, that doesn't have a memory address. That doesn't need a memory address. So that one could be shorter. And how about, the engineer said to the programmers, what about if like you could add 2 regions of memory and store it in a third? And the programmer said, oh, you mean like with one instruction? And the engineering guy said, yeah, why not? And then the programmer said, oh, that would be fantastic. Well, of course, that would mean that the instruction, a single instruction, would need to contain 3 memory addresses for an add. It'd have to be, one of the address of one of the operands, the address of the other operand to be added, and the address of the location where the result would be stored. Well, memory addresses take lots of bits in order to address a region, enough memory. So this kind of instruction would be really long. So what evolved was, and this was a major break, was the notion of variable length instructions. We started off with fixed length instructions on our very simple machine, where most of the instructions were memory reference and only referencing one piece of memory at a time. Load from this memory, store to this memory, add from this memory to the accumulator, or and from the memory to the accumulator, as we've discussed. But as machines became more powerful, essentially because hardware prices were coming down, integrated circuits were happening, it was possible, it was practical to put more complexity into the systems. The programmers were demanding more features. And so if you were going to have an instruction which had 3 memory addresses in it, it was going to be really long, multiple bytes of memory. But if you had an instruction that was going to just say clear an accumulator, that could be 1 or 2 bytes. So we broke from this notion of fixed length instructions into variable length instructions. And at that point, all bets were off, because now we could make our computers very complex. They could have, for example, you could have an instruction that was a prefix byte that said, that opcode we had, well, here's a whole nother set of opcodes. So now we weren't limited to, 8 or 9 or 12 opcodes. We could have hundreds. It was practical to have many more possible operations. So the engineer said, okay, well, what are we going to do with all this power? And the programmers said, well, since you're asking, there's some other instructions we'd like to have. Like, how about we do a lot of things with linked lists? So how about an instruction to do linked lists? And the engineers said, wow, that'll take like a lot of manipulation. And the programmer said, well, yeah, what are you guys doing? Go, do that for us. And so the engineers said, okay, write that down, Harvey. We're going to go implement that. And then they said to the programmers, what else do you want? And they said, well, we do a lot of subroutine calling, and we know that when we call a subroutine, we need to save all the registers. But it's tedious to have to like push this register and push that one and then push the next one and push the one after that. And then before we exit, to pop them in reverse sequence. How about an instruction for calling subroutines where like we had bits in the instruction which specified which of the registers to preserve in the subroutine call? And the engineer said, oh, we like that. That's cool. Write that one down. So the programmers got very creative with the stuff they wanted. But then the engineers who left that, imaginary meeting went back to their own area and said, okay, now we're in trouble. How in the world are we going to arrange to implement instructions this complicated? I mean, these things have sort of gotten out of control. And remember that the very simple fixed length instruction computers were, for example, in the case of a PDP-8, they were contained on just 3 8x10 circuit boards that weren't very dense, that just had simple and OR gates on them, because everything happened in a single cycle. Well, that's one of the other things that changed. As these instructions got more complex, no way were you able, well, for example, in the case of pushing a specified subset of registers, well, this instruction was going to could take a long time to execute. One instruction, because the instruction would specify, some number of registers get pushed. So it's going to have all these memory cycles after it reads the instruction, all these memory cycles to push these registers in succession. And there's going to be a reciprocal instruction to pop some subset back off. So that's going to take many cycles. And an instruction for managing a linked list. There actually was such a thing in the VAX. The DEC VAX had a linked list.
Really? That's such a high-level primitive. I mean, golly.
Yeah, it was amazing how complicated these instructions got. Yeah. There were some that were like, the programmers said, well, we spent a lot of time trying to find the first bit which is set in a long run of memory. We want to find a bit. How about an instruction that just reads memory until it finds a bit set?
Oh, jeez.
And there is such a thing. There is that instruction. And so, for example, in the famous Intel x86 instruction set, instructions can range from 1 byte long to 17 bytes long.
Wow.
There's that kind of range. So the engineers who actually had to create a machine that would deliver this kind of power said, okay, look, we cannot...
Give us a break.
We cannot design hardware that, you know how many AND and OR gates it would take to do this?
We're not going to do your job for you, for crying out loud.
So what they said was, and it was probably an instruction like this pop multiple registers thing. They said, well, we now that we've got all these cycles that it's going to take, we need microcycles. We need something like a computer in the computer, which can be smart enough to implement very complex instructions. And so someone said, what are we going to call that? Well, we'll call it microcode. And it's like, oh, okay. So what they did was, and this was a revolution in computer architecture, was they dropped the idea of unbelievable rat's nests of AND and OR gates, essentially, to try to implement this ever-expanding, aggressive instruction set. And they said, wait a minute. Computers have sort of flow paths. There's an adder that can get its data from different places, and there's a memory buffer that has the contents of memory, and there's maybe a multiplier that has its input. So imagine a very different kind of instruction word, probably long, many bits, but the bits in this so-called microcode, they just enable the flow of data along these different data paths at different times. And so just by sort of opening and closing these data paths in sequence, we can implement a complex instruction in multiple small steps. So the outside world still sees it as a single instruction. Inside, the microcode has many small steps which it goes through to pull off this complex instruction. So the programmers don't see it on the outside, but the engineers who engineer the microcode, they came up with a whole new way of thinking about how to engineer a computer.
I always assumed that all processors had microcode. I didn't realize that was a later invention.
Yeah, it was something that was developed through this necessity of they just couldn't. It's like how are we going to do this with just and OR gates?
Right.
And so the idea was that you'd have the so-called micro store was very fast because it had to run in like much faster than main memory. Main memory was chunking along, just reading instructions, but the microcode had to run many times faster in order essentially to have all those little microcycles fit within one major instruction cycle in order to get the job done. And that also meant that the instructions no longer all took the same amount of time. As we said, some more complex instructions would take more time. But that allowed this flexibility of instruction length. For example, the microcode, if you were doing a fancy operation like adding two words both in main memory and storing them to a third, that was no problem. Now, you just, that instruction had many more microcode steps in it in order to get the job done. And so this really changed the way the system was working, the internal design of the computers. And so what that also, of course, did was create a renaissance in complexity, because when the programmers heard that now there was like a computer in the computer, then they went hog wild with instructions they wanted. Because it was like, it's very much like, we all have heard the slogan the Apple has, there's an app for that.
Right. There's a microcode for that. There's an instruction for that.
There's an instruction for that. Anything these programmers could think of, they'd say, hey, how about one that does this?
Right.
And the engineer said, you really need that? Oh, yeah, I needed that yesterday, and I wish I had that. Okay, fine. Well,
so it does operate faster if you put it in the microcode in the chip than if you wrote it. It's easy to write a linked list in a higher level language or even assembler, but it's faster if you put it in microcode.
Well, and see that the perfect question, because remember that main memory was still very slow, and it was very expensive.
Got it.
So what had happened was computers turned into interpreters.
Right.
It was
to save memory.
Well, exactly. So what you had was super powerful instructions that then inside the computer it ran around and pulled it off. But that meant that you were saving main memory and you didn't have to fetch it that often. That is, if fetching from memory was time constrained, and it was because main memory was slow still, then, it was core. Remember, every time you had to read, reading was a destructive process. So then you had to rewrite what you'd read, because reading, the way to read from core is to set everything to 0, and you see where pulses come out in the cores that switched from a 1 to a 0, meaning that those were 1s. Before you set them to 0s.
Now they're nothing.
Now they were nothing, so you had to reset them to 1s again.
Holy moly.
So this gave a lot of opportunity for the microcode to run much faster, and it meant that your code density in main memory was very high. Essentially, we'd created an interpreter, and we know that an interpreted system allows very dense interpreted instructions where the instructions themselves are doing a lot.
Ironically, we do have a constrained hardware environment these days with mobile devices, with cell phones, and they, for the most part, use interpreted virtual machines to save space.
Well, so yes, what happened was, as technology moved forward, memory became faster, and more than that, it became cheaper. We just got better, production rates, and we got more clever, and we began to not be memory constrained. And at some point, some engineers said, let's profile actual code that's in the wild, out there that's running. Let's analyze the code and see what instructions are being used. The other thing that had happened during the same period of time is compilers came into use. Back in the beginning, it was the programmers writing all of this in machine language / assembly language that said, oh, I'd love to have an instruction for doing linked lists, then I wouldn't have to be writing that all the time. And so over time, compilers came into play. It just made sense to create a higher level language that itself would then create the assembly language, machine language that would drive the machine. But here was a problem. Compilers, it turns out, couldn't make use of all this fancy stuff. The compiler, the nature of the compiler, you see what I mean?
Yeah.
Humans could, but the compiler was like, wait a minute.
I want to do that.
Yeah. It didn't make sense. What had happened was instruction sets had become very specialized.
Right.
And individual.
So it's great for assemblers, for people who write, like you, who write machine language, but not for a automated system.
Not for a mechanized code generator that would sort of always be using the least common denominator. And so,
well, that's a good point too, since not every chip would have that capability.
Right. So when the computer architects of the past profiled the actual instructions that were being used, they discovered the familiar 90-10 rule. 10% of the instructions were used 90% of the time.
Right.
And then they said, wait a minute, if these fancy instructions are not being used, look at the expense in this machine for a linked list instruction, or these wacky bit search nonsense that we ended up getting talked into by the programmers. Compilers never use these. Yet, even though they're not using them, they're in the machine. Every one that we push out the door has very expensive to implement instructions that nobody uses, because we fired the assembly language programmers and we hired Fortran programmers or COBOL programmers, and the compilers now do the job that the assembly language guys used to do, and the compilers aren't using any of these instructions, which every single time we push one off the assembly line, we're paying for all this microcode store to implement things that no one's using. So there was a complete rethink at that point. And
where does this happen? Does it happen in Intel or is it happening elsewhere?
It was happening it was happening in universities, actually. The Spark came from Stanford and Sun, or Sun later, and the MIPS RISC machine was at Berkeley, and the ARM from Acorn was in the UK. And so that's where this notion, they said, hey, let's reduce the instruction set complexity. And someone said, ooh, RISC, RISC, reduced instruction set complexity. or reduce instruction set count, it's sometimes known as. The idea was that they realized they'd sort of gotten way off track with these incredibly expensive instruction sets, because they said, wait a minute, let's hold on. Let's instead kind of go back to where we were. That is, let's have very simple instructions, which now that main memory was fast, had caught up in terms of the speed we needed, and it got cheap. The other thing is that memory costs dropped through the floor. So you no longer had to have, an entire operating system and 20 shared time-sharing partitions all fitting somehow into 64K, which actually was done once. No, now we had, at this point, megabytes of memory easily, so code didn't have to be as dense. And essentially there was this wave of simplification that said, wait a minute, let's go back to. The other thing is that, remember, we went we had variable length instructions. Well, the only way you could handle a variable length instruction was in microcode. Having, microcode that knew that, oh, look, this particular opcode requires these different parameters, so we got to go fetch those now. And that means this instruction has more bytes after the opcode of parameters for the opcode. Well, all that was thrown out the window. They went back to a radically simplified architecture. One of the most popular is called a load store architecture, which is now currently today the most popular of architectures. The idea being that you have exactly one instruction for loading something from memory. You have exactly one instruction for storing something into memory. And all the other instructions deal with a much richer set of registers. Maybe 32 is the number that most of these architectures have now. So you've got 32 registers, and you can do things like add register 1 to register 2 and store it in register 3. You cannot add register 1 to the contents of memory. That just the other thing that, again, in a code analysis, what was seen was that wasn't being done that often. So they said, okay, let's try a whole different approach. Instead of like having all instructions able to add and subtract and multiply and do things with main memory, let's have a load instruction and a store instruction, and then everything else, our jumps and our branches and our math and logical things, those only work with the contents of what's in the registers. And we're going to have, that allows us to go back to a fixed length. And that means that every single instruction, like back in the old days, is a single cycle. That is one cycle. So now that main memory can catch up, or if not, then, caching had come into vogue. So then there was this notion of, they noted that programs tend to sort of stay in the area where they're executing a lot. And so the concept of caching came in order to provide a RISC processor that was able to ask for an instruction every single cycle, because it was able to execute an instruction in a single cycle. It was able to, the cache would feed the instructions at that rate. And so the idea was lots of little simple instructions executed very fast. And then other things could be done. Like if you knew that the instructions were all the same length, you could fetch a block of them ahead of time and bring them into the cache so that they were ready in case the processor wanted them. So that's there's a little bit of like coming back where we came from, but with a much more mature understanding of how to get the most bang for the buck. And the major thing that happened is that this rethink of architecture allowed for a dramatic simplification. Now, Intel was, and even to this day, is stuck with this insane instruction set, which I happen to know by heart.
Yeah.
And
the x86, they wanted to get out of it. They wanted to stop.
Yes, the x86, with its variable byte length between 1 and 16 bytes, they're stuck. The problem is, the reason they're stuck is backward compatibility. It matters too much. I mean, they've always wanted to like break free, but how can they ever do an incompatible chip? That like didn't run everything,
right?
And it's they've just
in fact they were going to, and AMD was the one that put the screws to them by saying, well, we're going to keep doing x86.
Exactly, yes. And so what happened was, it was, for example, a company like Acorn back in the late 80s that was trying to come up with a successor. Acorn was the preeminent personal computer company in the UK. There was Sinclair, and then and Commodore, and then also some U.S. companies had strong sales. But Acorn was the number one. They had a system based on the 6502, which was originally the processor technology. I'm sure that was the company, although processor technology was a different company also.
Yeah, there was. Oh my! It's funny how blurred it all gets together. 6502 was in the Apple II and the Atari. I remember.
Oh yeah, exactly.
A crappy chip, by the way. The worst instruction set. Oh,
careful there. You go.
I like the 68,000 instruction set, the Motorola instruction set. That was a very clean.
That was a whole different generation. That it's really not fair.
It was. You're right. Oh no, I know. But even the Z80, I think, was a little bit cleaner than the 6502.
Well, that too was a different generation. What the 6502 was incredibly inexpensive.
Right.
And it had a beautifully designed
MOS technology.
That's it. MOS technology. Thank you.
Thank the chat.
It had MOS being metal oxide semiconductor, of course. It had a beautiful instruction set, and what that allowed was it had just enough to get the job done, which meant it had a low transistor count, which meant it had a small die size, which meant your yield on wafers of the time, that is, you got many more processors per silicon wafer because the individual dies were so small because the transistor counts were so low. And that made these processors incredibly inexpensive. And that's why Commodore, Apple, and everybody jumped on the 6502. So what the Acorn guys did was they took a similar approach because they'd been 6502 users. They took a similar approach to a brand new design, and they were going to do a RISC processor. So naturally, they called theirs the Acorn RISC machine, ARM.
Oh, my goodness.
And
I had no idea.
And they ended up with a beautiful, lean design.
Right.
It was the small transistor count. Now, the other thing that is expensive in large dies and large transistor counts is every transistor you've got not only takes up space, but it takes up a little bit of power. And so the other problem Intel has been fighting valiantly all along is they've got this insane instruction set that they can't get away from, which they're trying to make faster and faster somehow. The problem is they are just dogged by power consumption because this complex instruction set requires a huge amount of power. I mean, like disproportionately so, just to feed the latent complexity in the instruction set takes its toll. Whereas the ARM, the Acorn RISC machine chip, because they had the idea. I mean, they came a little bit after the SPARC and the MIPS, so they were able to learn from those designs. But they also came from a 6502 era of understanding low complexity. And interestingly, they were a small company with a small design team, and they didn't have fancy tools. So they also had no choice but to do a simple, small RISC machine. Well, even though it couldn't compete then with the SPARC and the MIPS, it competes now because of its low power consumption. And what happened was, in the evolution of Acorn, they ended up renaming themselves Advanced RISC Machines Limited, again, ARM, and they're a licensing company that licenses the intellectual property of the ARM RISC core and allows other people. They don't produce them themselves. That's why, for example, Qualcomm has the Snapdragon, which is an ARM-based chip. And it's why Apple, with their A4, is an ARM-based chip. So Advanced RISC Machines is an intellectual property licensing company licensing this beautiful core, which has, because of it was always an efficient design, but it was a small design because it's the only thing they could design. But small means very inexpensive, just like it did on the 6502, and it means there just aren't that many transistors. The first ARM had only 25,000 transistors, compared to now you've got hundreds of millions of transistors. So you had very low power, and because it was a relatively state-of-the-art design, the right architecture. And that's why everybody who's doing handheld devices has ARM-based technology.
Makes sense.
Because you get a lot of you get the processing power you want, but and it's inexpensive because it's a small die, and it's inexpensive in power consumption because it doesn't have that many transistors hungrily burning up power, and the ones it has are all in use. The other problem with the Intel instruction set is, as we saw, it's inefficient due to the 90-10 rule. So you got all these transistors sitting around not doing much, because they just end up being the exception rather than the rule. Whereas this lean RISC design has all your transistors busy all the time, so that's efficient too. You get a lot of use for out of the power that the transistor is using. And that's the story of RISC
I love
processors.
it. And very timely, because, of course, here we are sitting looking at RISC processors all the time now in our phones, in our iPad, and all these small devices.
Yep.
Android, which is originally running on an ARM processor, is being ported to the Intel Atom processor so that Google TV can run on an Atom-based system. Of course, it runs on a Java virtual machine, so it's probably a simple port to make. You just need a virtual machine to do it. But I wonder what kind of efficiency hit they're going to take.
It'll be interesting to see. In 2 weeks, what I want to talk about, and this is I think this exhausts me in talking about technology, is the need for speed, because there's a fascinating story that's the last thing I want to cover on what has been done inside these machines to give us the speed they have.
Ooh.
People are not going to believe that. I mean, it just grays your hair to think of the engineering that has gone into this. We're going to talk about pipelining and multiple issue and out of order execution.
Oh, I love that stuff.
Branch prediction, superscalar stuff. I'm going to lay that out. And at the end of that episode, everyone's just going to look at their little, their iPod or their pad or their phone and think, that stuff is in there.
Yeah.
And I mean, it makes you appreciate I'm just stunned by what went into the technology that we so easily take for granted today.
It's really true. It's so complex, and yet it works.
It does.
Yeah. Fascinating stuff. I hope everybody who's interested knows about this and listens, and tell your friends if you think they'd be interested. Steve Gibson is the guy in charge at the Gibson Research Corporation, grc.com, if you want to find his SpinRite program and all the free stuff he gives away. He's also blogging now, steve.grc.com. and heaven forfend, heaven, amazing, hell hath frozen over. He's tweeting at SGGRC or at SGPad for iPad stories or pad stories in general.
And for what it's worth, the followers of my tweet stream found out about the flash problem immediately.
That's a good way to find this stuff. It's a good early warning system.
Yes.
It really is. I think of it almost as a nascent internet nervous system where, this stuff just goes out.
And also people who want to listen live learned that I was going to be on Thursday instead of Wednesday. Same way.
That's true, too. Follow him on Twitter at SGGRC. Steve, next week we will do Q&A, so if people have questions or comments or suggestions, they should go to grc.com/feedback.
Please.
Yeah. And if you want the 16 kilobit version of the show, Steve makes a version of that available along with transcripts and show notes at his website, grc.com. So that's another reason to head over to the GRC site. And Steve, we'll catch you next week.
Talk to you then, Leo.
Security Now.
Today, I feel the need, Mr. Gibson, for speed.
Well, so we've established the original technology of computers, looking at the way, for example, early mini computers like my favorite old PDP-8 operate, where memory is a bunch of words and the words are broken into fields of bits, and the bits specify, for example, the opcode, the operation code, what that word of instruction is going to cause the hardware of the machine to do. And even then, even though the machine went from one instruction to the next, the execution of that instruction internally took several phases. You would fetch the instruction from main memory into we talked about the IR, the instruction register, where the machine would then look at the opcode to determine what this instruction was telling it to do. So there was a fetch of the instruction. Then there was a decode where you decode what it is that you fetched. Then comes to execute the instruction, whether it's incrementing the accumulator or adding a register to another, maybe jumping to somewhere else. And then in some cases, you would be writing the results back, maybe writing the result of incrementing the accumulator back into the accumulator, or writing it back into main memory if you were storing. So from the programmer's view, the programmer sees this as atomic events, one instruction per word. The engineer who's designed the computer to do this sees that there's more going on. There's, a single execution of an instruction actually requires many different phases: fetch, decode, execute, and then write back the results. So machines were being produced like that, and people naturally wanted them to go faster. And what the engineers saw was that, we fetched an instruction, then we're decoding it and we're executing it. But while we're doing those things, we're not using main memory. That is, it's waiting for the next fetch. And so the concept dawned on them, and this actually happened in the mainframe level in the late 60s. This notion of sort of overlapping things, and the best example, I think the model that's clearest is, because we've all seen examples of it, is the automobile assembly line, where which, as I understand it, Ford invented to create his cars. The idea
Just a
being,
side note, by the way, we're going to be going to visit the Ford assembly line on July 30th.
We?
Me.
Oh,
Me.
cool.
Yeah, and I'm going to bring the live camera, and we're going to actually show the state of the art in modern assembly, which I can't wait. They're
I
Dearborn
would love
plants.
to see that because you only get little snapshot snippets of pictures with robot arms swinging stuff
I know,
around.
I'm so excited.
There. That would be really cool.
I'm going to go see where my Mustang was born.
So
Anyway, sorry, didn't mean to interrupt. Go ahead.
so the idea with an assembly line is that at every stage of assembly, you do a little bit of work towards producing a finished car. The time required to produce one car is the time it takes to go the length of the assembly line. But once the assembly line is full of partial cars being assembled, the rate at which cars come out is much faster than the total time it takes for a car to move through the assembly line.
Wait a minute, let me think about that. The cars come out faster than it takes for a car to go through the assembly line.
Yes. So say that you had an assembly line of 10 stages.
Yeah.
And that each stage took a minute.
Okay.
Well, when you start making a car, if
10 minutes.
It's going to take 10 minutes for that car to go all the way through the assembly
but then
line.
cars will come out one every minute.
Exactly. Once the assembly line is full, then they come out every single minute.
Got it. Okay. I'm glad. Sorry, I'm stupid, but I needed to understand that. Okay.
And so in processor technology, we call this a pipeline. And virtually every machine now being made, and actually made for the last 2 decades, has been pipelined to one degree or another. So let's first apply that to the very simple model of this machine which fetches, decodes, executes, and writes back. The idea with a pipeline there would be that you fetch an instruction, then you start decoding it. Well, while you're doing that, memory is free. You're not using memory. So most instructions, most code is sequential. That is, we know that after normal instructions are executed, the program counter is incremented by 1 to the next word, which is then fetched, and the one after that, and so forth. That changes in the case of jump instructions, which jump us to somewhere else, or branch instructions, which may or may not branch to somewhere else. But in general, it's a safe bet that we're going to be moving forward. So the engineers who wanted more performance out of the system, basically, and this will be a recurring theme through this podcast, you look at the various components of your system and think, how can we keep them busy all the time? How do we, get the most performance out of it? Well, it's by keeping all the pieces busy. So if while we're decoding an instruction we just fetched, we assume that we're going to be executing the next one here in a while, well, go ahead and fetch it. Get it read from memory. And similarly, after that first instruction's been decoded, then it's time to execute it. Well, meanwhile, at that point, the decoder is not busy because it just did its work on the first instruction. Well, now we've got the second instruction that we fetched while the first one was being decoded. It can now be decoded. And so the analogy is exactly similar to the assembly line, where instructions move through several stages, and once they get going, rather than an instruction having to go all the way through and before you even start on the next one, you're able to make some assumptions that allow you to basically create an assembly line for computer instructions, just like you do for cars. Now, it gets from that simple sort of start, then things really get interesting, because one of the things that happens is that instructions may interact with each other. That is to say, if we were to add two registers, say that we had a machine with multiple registers, as all contemporary machines have now. Back that PDP-8 had just the one accumulator, and which you sort of ended up using as a scratch pad. Now we've got 8, 16, 32, lots of registers. So say that an instruction that you read was adding two registers together, that is, adding one into another, and that the instruction that followed took the value from that add and stored it. Well, so now we have a problem, because we have instructions in this pipeline which interact with each other. So over time, engineers have made these pipelines longer because they'd like to get as much simultaneity going as possible. But they've also had to deal with the fact that there can be interactions, and often are, between instructions that are in the pipeline at the same time. So the first thing that's done is that instructions are broken into smaller pieces. They're called micro ops. So, for example, say that we had a simple instruction. We've talked about how the stack works, how, for example, when you push something on the stack, what happens is the stack pointer is decremented to point to a new lower location in memory, and then the value that you're pushing is written to the location where the stack pointer is pointing to, in this scratch pad. So that operation, a single instruction, push a register, can actually be broken into two micro operations. The first one is decrement the stack pointer. The second one is copy the register to where the stack pointer is pointing. And imagine another instruction, like adding a register to what's in memory. Well, to do that, you have to read out what's in memory, then you have to add the register to what you read out, and then write that sum back to that same location in memory. Well, that's 3 micro operations. So what the processors do now is they take these sort of the programmer sees them as instructions, but they're actually complicated enough that they can be broken down into smaller pieces. So the processor fragments these single instructions into multiple micro operations, and then basically pours them into this pipeline, which is getting increasingly long. In some cases, as long as like 20 stages of like staging of instructions. Now, one of the things that engineers noticed was that some instructions, like this, imagine this read, and imagine the instruction I talked about where we're wanting to add a value to something in memory, where we're having to read the thing out of memory, then is it sort of into some internal temporary location that isn't even named. Then we add a register to that and then write it back out. Well, so we've taken that single instruction and broken it into these 3 micro operations. Now imagine that there's an instruction behind it. That is, it actually is later in the code that's doing something else entirely. It's adding 2 registers that aren't related to these micro operations. What the engineers realized was, while the computer was out fetching the value to be added to, it had already fetched more instructions behind, and the ones it had behind were independent of the outcome of the instructions that it was working on currently. And, for example, while fetching something from memory, the machine's adder the ALU, the arithmetic logical unit, was idle. So the processors of today are able to realize that they've got other things they can be doing and which are independent of the outcome of earlier instructions. So why not execute them out of order? That is, literally rearrange these micro operations in the pipeline so that things that are taking longer can literally be passed by instructions which can take advantage of resources in the chip which are not currently in use. And so what we've ended up with is this amazing technology which pours instructions in the front end of the pipeline, fractures them into smaller sort of individual granules which need to be executed in order for that to happen. Then logic which is sophisticated enough to look at the interdependencies between these micro operations and reorder them on the fly so that the assets that the chip has, like arithmetic logical units, like a floating point processor, like instruction decoders, all these assets are being maximally used. And in fact, one of the things that happened was that processors went so-called superscalar. What I described so far is a scalar processor. A superscalar one is one which is actually able to execute more than one instruction per cycle. That is, normally you would be retiring instructions when you're done out of this pipeline sort of at a given speed. Well, if you have enough assets to execute instructions, there's no reason you can't go faster than 100%. And so superscalar processors go faster than 100%. They've got, for example, there are some that have 4 ALUs and 2 floating point units. And so they're literally able to be doing 4 additions at once. Sometimes those are part of a very complex instruction, or sometimes they're part of different instructions. The point is, the processor has become smart enough to break all of these down into little sub-functions and then sort through them, analyzing the interdependencies among these sub-functions and taking advantage of anything that might require a delay in order to say, oh, wait a minute, we've got a guy back further here who isn't dependent upon any of our outcomes, and we've got a free adder. Let's do that addition right now. And if you think for a minute about the logical complexity of any instructions which you might encounter and having to, on the fly, I mean, we're talking, there's no time to do this either. This is not slowing things down. The goal is to speed everything up. So you can't even catch your breath. This is all happening, billions of times a second at gigahertz speeds. This is all being managed. So now we have a system which is able to do literally sucking instructions in, cracking them down, rearranging them on the fly, looking at interdependencies. Well, that wasn't enough for the engineers. Management said faster, faster, faster. And so the engineers are like, well, wait a minute, we're going as fast as they can. Well, what they realized was that wasn't true, because there were still a way they could get a little more clever. When I used the word retiring an instruction before, and that's a term used in this art where you finally say you write the results of the instruction back out. So inside this pipeline, you've got an amazing amount of resources. You've got unnamed registers. By that I mean they're not like the register 0, register 1, register 2, or AX, BX, CX. That is, they're not the registers the programmer sees. These are like temporary scratch pad registers, which are not visible to the outside world, not visible to the instruction stream, but they're used, for example, if you were adding something to memory, well, you've got to read that into somewhere in order to add something to it. So that's an unnamed register. So it's when you retire an instruction, you're sort of writing its results back out to like the real registers, to the programmer accessible registers. But the engineers realized that in some cases, they did have a result which a later instruction was waiting for, even though they hadn't yet retired the earlier instruction out to, for example, writing to like the AX register. They did have it in the pipeline. So they added a whole nother layer of nightmare by allowing results to be forwarded, and that's the term that's used, within the pipeline to like track this so that partially executed instructions which had not yet been retired could have their results sent sort of back into the future in order to allow instructions that had stalled because they were dependent upon an outcome which hadn't been resolved yet. And all of that exists also. So what we have now is something unbelievably complicated. Now, what happens if you hit a branch? Because branching, any change of linear flow, is the worst possible thing that can happen. Think about it. We've got all this happening. We've got 20 instructions maybe that have been taken apart, all under the assumption. Remember, we made one fundamental assumption at the beginning, which was we're going to go linear. All of this sucking in things ahead of where we are assumes we're going to use them. All of this work says that we know where we're going, except when we come to a conditional branch or even a jump that's going to go somewhere, suddenly everything changes. We now don't know whether we're going to keep going or go somewhere else until later in that instructions phasing. Remember, now instructions are being cracked apart, they're being decoded, they're being executed. There's like all this work being done before the outcome of the instruction is known. The problem is, if it's a branch instruction that might change the sequence, if it does change, if it's branching us to somewhere else, well, everything behind that instruction has to be scrapped. So the entire pipeline has to be dumped, and we stall until we are able to then load a series of instructions from the new location and sort of get all this going again.
And that's what screwed up Prescott, because I think their prediction wasn't good, or their pipelines were too long, and they had a lot of dumps.
Well, yes. So having developed this amazing complexity for dealing with, just incredible acceleration of performance as long as you go straight. The second you change away from that's linear execution, you're in serious trouble. So engineers realized that branch prediction was crucial. That is literally being able to guess without knowing what a branch was going to do. The way they've come up with doing this, there was a first level you can imagine a simple-minded way, which says, okay, let's assume that the branch that we encounter, if we've ever encountered it before, is going to do the same thing. So that sort of makes an assumption that branches generally do whatever they're going to do. In fact, microprocessor designers realize that many branches that are branching backwards are at the bottom of a loop, in sort of a loop of code, which tends to get executed a lot and then finally isn't executed. So a branch backwards tends to be taken as opposed to a branch forward. So there was some simple-minded sort of branch guessing that way. Then they said, well, wait a minute, let's record the last outcome of the branch and assume that it's going to do the same thing again. So an early branch predictor simply did that. And the idea was that you would take a chunk of the lower address bits, so like the least significant address bits in the instruction counter, and you would for every one of those address bits, you'd create a table that had a single bit in it, which recorded a branch at this location did the following thing last time. It was taken or it wasn't taken. Now, we're not talking about having a bit for every branch in the computer. We're saying that we're going to have a sort of a bit, maybe 256 bits for like the lowest byte of the instruction. So branches could collide with each other. A branch that was exactly 256 words further down would end up having the same least significant byte of address. So its bits would collide with each other. There's nothing we can do about that. But the probability of that is relatively low. And so there was always this cost versus performance trade-off that's being made. But the engineers weren't happy with just using a single bit, because imagine that you had a branch which in the code literally alternated what it did every other time. It turns out that's also very common. Well, that would literally mean that every prediction you would make was wrong. If you remembered what it did last time and you assumed it was going to do it again, and this branch, the logic in this branch was in every other logic, then you'd always be guessing wrong. And so the performance would just be abysmal. You'd get no benefit from your pipeline. You'd be constantly dumping the pipeline and then needing to refill it. So the developers came up with a 2-bit branch predictor, which they call a saturatable or a saturating counter. The idea being that, so 2 bits could obviously have 4 states. You could be 0, 0, and then if you count up, you go to 0, 1. You count again, you go to 1, 0, and again you go to 1, 1. So those are the possible values. So the idea of a 2-bit branch predictor was that if you took the branch, you would increment this 2-bit counter, but never more than 1, 1. So that's the saturating part. It would saturate, it would go to 1, 1, and then just stay there. If you did not take the branch, you would decrement the counter and down to 0, 0, but then you never go below 0, 0. It saturates at the bottom end also. So what this gave you was a better sort of more of a probability. You could, if you generally took the branch, but not always, this counter would still make a mistake, but it wouldn't change its mind completely. So if you generally took a branch, even if you occasionally didn't, it would still remember that you generally took it. So it would generally be guessing correctly. And so that increased the performance of branch prediction substantially. But there was still a problem, which was that there were patterns of branching which this simple-minded 2-bit predictor couldn't handle. And so in real-world applications, it was better than nothing, way better than nothing. But some other engineers realized, hey, we can do something even more clever. We can do a 2-level prediction. So what they created was a shift register of bits, which was whether the branch was taken or not in history. And it wouldn't be very long. Maybe, let's say for a discussion that it's only 4 bits. It's only 4 bits long. So the shift register is remembering whether branches are actually were taken or not. And every time we come to a branch, we first of all look at the least significant byte of the address to choose one of 256 whole worlds. So each possible location in memory with this 256 cycle has its own entire little branch prediction world. Okay, so within that world is a 4-bit shift register that remembers for that branch or branches at that location in memory whether the branch was taken or not. Okay, those 4 bits, we know that 4 bits gives us 16 possibilities. Those 4 bits are used to choose one of 16 of our little 2-bit saturating counter predictors. And what we end up with is literally pattern recognition, where over time this acquires a knowledge of any sequence of up to 4 long of branches and not branches being taken. That will be recorded in the 2-bit predictor, which will tell the computer with very good probability whether the branch will be taken again or not. And these predictors have grown in length and in size. And so remember that there's one of these whole predictors for each of a number of different locations in memory where these branches could fall. So now what we've done is we've got this pipeline sucking in instructions, cracking them down, looking at their interdependencies, reorganizing them on the fly, taking it, we've decoupled the arithmetic logical units and the floating point processors and the instruction decoding and all of this so that those are all now separate resources which are being assigned and used as soon as they can, as soon as we're able to see that we know enough to allow one of these micro operations to proceed, we do. At the same time, the system is filling up the pipeline at the top using the results, assuming we're going linearly unless we hit a branch or a jump, and then recording the history and literally learning the pattern of the past sequence of branches in the code and sort of heuristically developing an awareness, a pattern recognition of whether so that it's able to guess with as much as, it turns out, 93% probability whether a given branch will be taken or not, only missing about 7% of the time. And when it's
is that
wrong,
the average for all processors, or?
Yes, state-of-the-art prediction now.
That's amazing.
I know. It's just
That's amazing. It's like that old joke. How do it know?
Yeah.
It's like predicting the future, really.
It's like 6.75% misprediction. So about 7% misprediction. 93% of the time, they're able to guess right.
Wow.
And so making a mistake is expensive in prediction, because we have to flush all the work we were doing and then go somewhere else. But 93% of the time, we're able to get it right. Now, before we get to the next feature, okay,
may I interrupt you?
by all means.
We're doing great, but I just want to get one more commercial in before we get to the improvements that have been made more recently. Because it's you would think now, hey, this is magic. This is all you need to do.
We still got a couple more.
We still got some more magic ahead. But speaking of magic, I want to tell you about a great place to go to make your website, your magical website. If you're looking to move off of Blogger or WordPress or TypePad, if you're looking for a host that has incredible content management software, look no farther than Squarespace.com. And I say that because we are very happy Squarespace users. We use it for the Twit blog. I'm moving my radio show. This is how good it is. I'm moving my radio show site over to Squarespace.com. Something I should have done a long time ago, to be honest with you. But I'm old habits die hard. But I've just watched more and more of my friends, Kevin Rose, Lisa Bettany, Sarah Lane, move to Squarespace.com. I've seen more and more happy customers send me emails, and now I'm realizing, but I should have been doing this forever. You should too. Why? It gives you full control over your site, and your site looks gorgeous. You can customize it beautifully. Build it fast, and it runs fast. With Squarespace's VPS, Virtual Private Servers, this technology using Java is amazing. Gives you bandwidth when you need it. Scalable, kind of almost infinitely. You get seamless blog importing, so if you've got a movable type WordPress, TypePad, or Blogger blog, it could just boom, take that stuff in. And by the way, and this is something I really believe in, is true data portability. You can export it too. You're never stuck. Try it right now free. You don't even need a credit card. 15 days free if you go to squarespace.com/security now and take a look. I do recommend, if you're, there's a great tour on the site, but if you're interested in what a Squarespace site looks like, one of the things I've found is that, WordPress, you can always tell you go to a Drupal site or a WordPress site, you're saying, I know what that is. There's a certain look, not with Squarespace. Look at these example sites, and you'll realize every Squarespace site is unique, because Squarespace, even though you start with these great templates, lets you do anything you want with CSS and JavaScript. So you even if you don't know any design, you're going to start with a great template. And then as you, look, here's our site. We're on there, inside.twit.tv. As you improve your technology and your abilities, so does your website. Squarespace.com/security now. The free trial for 15 days, absolutely free. You don't even need a credit card. And if you decide to buy, use Security Now as a coupon code, and you will get 10% off for the life of your site. That's a really good deal. It's not a lot at first because Squarespace sites are very affordable. They start at $8 a month. So, okay, you save 80 cents a month. But this is forever. And you can upgrade from the basic to pro, advanced, business, and even community. And even at the top line, it's very affordable, a lot less than we spend for our servers. You get hosting in the cloud, visual style designer, amazing statistics, content management that includes an iPhone app, great support for social media, and more for a very affordable price. If it's time to set up a website, if you're ready to get a better site, if you're tired of your site bogging down with a twit effect, squarespace.com/security now. It's the place where great websites start. Back to our conversation. Steve Gibson is here from grc.com. He's the man behind SpinRite, that great software for hard drive maintenance and recovery, and a lot of great security tools. Somebody's asking in the chat room, this isn't security. Well, in a way it is. This is a series Steve's been doing all along on the basics, the fundamentals of computing. In fact, from day one on Security Now, you've really done a great job, I think, of getting people up to speed with these fundamentals, things you have to understand security, right? These are not completely incidental to security.
It certainly is the case that everything is interrelated. For example, I'm thinking as I'm working toward getting going on CryptoLink, the VPN product that I'm going to do next. Well, encryption performance and decryption performance is very important, and understanding the internals of what the chip is doing really does allow a developer who wants to truly optimize their code to arrange the instructions so that the logic in the chips have the most latitude for working. And, certainly performance has been something that we've been questing after forever.
Yeah.
So
and we're getting it with this amazing pipelining and parallelism and so forth.
So the engineers have got this incredible pipeline built. They've got now this amazing branch prediction system. And then they realize that they've still got a problem because they suck in a return instruction into the top of the pipeline. Well, we know from having discussed this before what a subroutine return does. When we call a subroutine, we're using the stack. We decrement the stack pointer and put the address of the instruction after the call on the stack so that later, once that subroutine has finished, it's able to do a return instruction which looks on the stack for where to return to, which has a beautiful effect from a programmer standpoint of bringing us right back to the instruction following the one which invoked the subroutine. Well, one of the first things the subroutine does, because most subroutines don't want to mess up what was going on when they were called, they'll push a bunch of registers value onto the stack themselves so that they can be popped off the stack and restored prior to returning. That allows them to have sort of those registers to work with and then not mess up what was going on in the main code that called the subroutine. Okay, so with that in mind, visualize what's going on in the processor now with the pipeline, where the pipeline is full of the instructions toward the end of the subroutine, and then the subroutine is finished and it does a return. Now the problem is that the return uses the value on the stack, but the thing that the subroutine is doing just before it returns is cleaning up its registers, getting their values off the stack in order to restore them to what they were, and this is happening further down in the pipeline, which means the stack pointer is going to be changing a lot, and there's no way we can execute any of the return instruction until literally we know what the stack pointer is going to be, and then we have to go read where it's pointing, get that value, that tells us where to return to, so then we start fetching instructions from there, which means a return instruction is deadly. It literally brings everything to a halt because we don't know where the stack pointer will be, because the instructions typically occurring, all of those instructions just before the return are changing the stack pointer as they pop the values of the registers back off the stack into the registers so that they're restored when we go home. So the engineers scratch their head for a while and they say, wait a minute. What we need is an internal call stack. We need our own private stack because we know that more often than not, subroutines nest perfectly. That is, some code calls a subroutine, which will return. Or maybe that subroutine calls a subroutine, but that one returns to the one that called it, and then it returns to the one that called it. In other words, there's a nesting which is almost always followed, which means that this incredible execution unit in the processor now maintains its own call stack. When it sees that it has been jumped to a subroutine, it records internally the address of the instruction after that call on its own little stack. There's no instructions to get to it. Programmers can't see it. It's completely invisible. The call stack ranges from 4 to 32 entries in modern processors now. And so what happens is, since the internal pipelining miracle has recorded this. The second a return instruction is seen, which is just a byte for example, in Intel instruction, it's just a 60 hex, a 60 hex. The second that byte is seen, the system says, that's a return instruction. We don't have to wait for anything. We can immediately pull where we know it's ultimately going to return to off of our own internal stack and continue without interruption, sucking in more data from the point we're going to be returning to without missing a beat. So that's another level of what was added. Now, once all of this was finished, and this was maybe, about a decade ago, we had this level of technology, there was still some unhappiness with the contention for resources. That is, there was still not what's called instruction level parallelism. There still was like the ALUs and the floating point units. They were sitting around not being used all the time. The engineers weren't able to get them busier because there was still too much interdependence among these micro operations that they couldn't get enough. They weren't able to use the resources fully. Well, this is when this notion of simultaneous thread execution occurred to them, which Intel calls hyperthreading. I mentioned it a couple weeks ago in passing. I couldn't do it justice because we didn't have enough foundation to understand what hyperthreading is. Well, we do now after the last 45 minutes of this. What hyperthreading is the recognition that there is what's called register pressure. There is not enough freedom of value assignment among registers. There's just too much interdependency. But if we had a whole second set of registers, if we duplicated everything, then where some micro instructions are fighting with each other, too interdependent, where they're having to wait for results to finish before the later ones can start. Therefore, assets like the arithmetic logic unit and the floating point unit are sitting around being unused. If we have another physical thread, that is, we have another whole set of registers, well, because it's a different thread, they're logically disconnected from the first thread's registers. There is no conflict at all possible between these separate banks of registers. So what hyperthreading does is and this, talk about it being confusing already, this literally pours instructions from two entirely different threads of execution down into the same pipeline, breaking them all up, keeping them all straight, realizing that these micro-ops and these registers are actually different from those micro-ops and those registers. So now we've doubled the opportunity for exploiting these fixed assets, the arithmetical logical unit and the floating point unit, being able to keep them busy much more of the time, which is what hyperthreading does. Essentially, it doesn't duplicate the entire system, but it allows us to pour two different threads of execution into the same pipeline and get a tremendous boost. I mean, it's not like doubling. We don't get double because the resources weren't that underutilized. Typically, it's about a 25% gain, which, in this quest for performance is better than a kick in the head. So lastly, with all of this this much industry having been expended in order to satisfy essentially CISC, that is complex instruction set computers, the guys designing the RISCs were just dizzy. They said, okay, wow, do we want to do the same thing? Are we going to basically duplicate this insanity? RISC architecture is different in a number of ways. Fundamentally, the RISC concept was designed to prevent there from being a lot of this kind of like available performance boost because the instruction design just doesn't get itself into trouble so much. One of the very clever things that RISC instructions do is there's something called conditional instructions and something called an explicit condition code update. Now, what that means is that notice that we have a stream of instructions that are being executed by the processor, and then a branch instruction is often skipping over some. There'll be something that like you don't want to execute in this certain case, so you jump ahead 10 instructions or 5 instructions or something. You're skipping over them, which is many times what a branch will do. What the RISC designers realized was, at the expense of some more bits in the instruction word, and it does widen the instruction word a bit, they could make what's called conditional instructions instead of branches. That there are still branches and jumps, and those are being optimized still very much the way they are in CISC instructions with branch prediction and so forth. There's no way around that. But essentially, the RISC guys said, wait a minute, if we just want to skip over 5 or 6 instructions, for example, if the result of an add was 0, or if the result did not overflow and the carry bit was set, why not add to any instruction some additional bits that say execute this unless the condition code is 0, which means that we've saved ourselves a branch. We don't have to branch over those instructions. We can make the instructions themselves just sort of skip over themselves. The instruction says, only execute me in this certain case. That is, the case where we wouldn't have taken the branch. So what this did was, this allowed a very aggressive forward fetching pipeline to go in a straight line, and we understand why pipelines like to go in a straight line. We were talking about that before. This allows the pipeline to fetch ahead, and even though it may not be executing instructions, it saves all of the possibility of a branch misprediction because we don't have a branch at all. Now, the other trick is, if you had a group of instructions which you collectively wanted to execute or not in a certain case, if you were executing them, you wouldn't want them to change like the state of the carry bit or the 0 bit or any of the condition codes, because then that would mess up the conditional execution of the instructions that followed. So the other thing that was added, in addition to this notion of a conditionally executed instruction, is the ability for the instruction not to modify the condition code when normally it would. You might be like doing some addition, and normally the add instruction will set a flag saying, oh, the outcome was 0, the outcome set the carry bit, the outcome was not 0, various condition code situations like that, where so what was done was a bit was added that said, do the add, but don't change the condition code, because we're wanting to continue the instructions afterwards along the same, to have the same effect as the one we just executed based on a condition code which was set deliberately earlier in the path. And so that was essentially the final optimization that the RISC guys brought into the design of the instruction set, which further made pipelines able to absorb this huge number of instructions, sort through everything, and perform really this overwhelming job of making processors incredibly fast.
It is such an amazing, mind-boggling thing, especially when you think that we're operating now at the microscopic at the level of a molecule's width in some of these newer 45 nanometer processors. It's truly amazing.
Yeah, and I would imagine that probably everyone listening to the podcast has at one time or another seen one of those very cool photo micrographs like that of a processor chip, sort of as if it was taken. It looks like a satellite photo of a city, and you look at that and you think, my goodness, look at that. I mean, you can just tell by the level of detail in there that an incredible amount of something is going on. Well, what we've just described is what that something is. That this technology is what has increased the power consumption, increased the size, increased the cost, but dramatically allowed the performance of these processors to increase. And this, what we described today, this kind of incredible out-of-order execution, branch prediction, internal call stack, register renaming, all of this is in all of today's processors. It's just being taken for granted now. It's the way we have the kind of performance that we do. Without any of this stuff, we'd be back with an 8088 running at 4.77 megahertz.
There was a really good book, it must be 10 years ago now, called The Silicon Zoo, where they had those little pictures of the stuff. Of course, It's so old now; it's changed a lot. But these photo micrographs, if you search for Silicon Zoo, they're still online. Some pretty amazing pictures. You can tell how old the site is, though, because it says, "Oh, this is going to take a minute at 28.8." It's a big image, but you can do a little Googling and you'll find it. Fascinating stuff, Steve. Once again, you've done a great job of explaining how this stuff works. And networking next, but next week we're going to do a Q&A, I think, yes?
Yep, we have a Q&A, and then I'm going to, many listeners have said, hey, Steve, I thought you were going to tell us about LastPass. We're using it, we want to know we should be, and it's safe. So that's queued up for 2 weeks from now. We'll do a Q&A next week, and then I'm going to explain in detail the cryptographic protocols for LastPass and how the whole system works.
Oh, great. That's great. If you have Q&A questions, grc.com/feedback is the place to go. He's got a feedback form there. GRC is a great place to go for not only SpinRite, the world's best hard drive maintenance and recovery utility, but also this show. 16 kilobit versions are there for bandwidth impaired fellas and gals. Of course, I love the transcripts. It's a great way to follow along. And I suspect more than one teacher is using your lectures on how computer fundamentals in their classes. So I think transcripts would be very helpful in that case as well. And you're more than welcome to do that. I hope that you understand you don't have to get our permission to use these podcasts. They're Creative Commons licensed. Attribution, non-commercial, share alike is the license. You can find out more at twit.tv at the bottom of the page there about our license. And you're more than welcome to use these. In fact, I think it's great if you do in courseware. Somebody was asking in the chat room. Steve is also the author of many great freebies, which you'll find at grc.com. And he's got a Twitter account now. Be careful. He's got more than one. He's got several. In fact, he's got the main account, which is at SGGRC. He's got the account. Are you still posting articles about tablets?
Haven't for a while, but I've when something comes up, I will definitely do that.
That's at SGPad.
Yep.
And then the corporate account at Gibson Research. That's all on Twitter. And his new blog, steve.grc.com. Did I get that right?
You did.
All right, my friend. God, I love this stuff. Fascinating stuff. Thank you so much.
Talk to you next week, Leo.
Take care.
Security now.